gonna share the screen, and hopefully in the last minute more people join in. Okay, so hello everyone. This is Taha Selim. I would like to welcome all of you on behalf of Bibliotheca Alexandrina, Alexandria Library, and iQafé. Today we have the fourth monthly series in quantum AI, and we have very distinguished speakers from all over the world, from Egypt, from Emirates, from Europe, and from United States. Friends, business partners, collaborators, and close connections. So welcome everyone. Before I start, I would like to introduce myself quickly. So I'm Taha Selim. I'm the General Manager of MolKet SAS. I'm also lecturer and researcher at Amsterdam University of Applied Sciences in the Netherlands. This is where I'm based. I'm also co-developer of a new master in applied quantum technology, which is a joint degree between 4 universities of applied sciences. I also have a research profile in quantum machine learning, physics-inspired AI for chemistry materials, and my background coming from quantum theoretical chemistry. I'm also a YouTuber, so I like to share some technology insights and reviews in tech, and a member of several international tech networks. And recently I've been invited to give a talk to Azure Quantum Field Ambassadors Network, and I was a co-speaker at different international talks and different conferences and networks. Before I start, I would like to give the floor to Youssef Eldakar to talk about the upcoming hackathon and make a few announcements.
Thank you very much. I'm Youssef Eldakar from the Library of Alexandria.
Yes.
I am head of the International School of Information Science, which is part of the library that specializes in supporting research through technology. We are involved in several things, one of them being the high-performance computing service that we provide to universities in Egypt. I'm very happy to see this effort grow since we started together with my very good friend, Dr. Taha Selim, in December. And it's nice to see this community become something quite significant. And since we started, we announced that we were planning a hackathon, which is part of our collaboration with the Open Quantum Institute. As the Library of Alexandria, we are a partner in the Open Quantum Institute. Currently, that's under CERN. The hackathon that we are planning is to take place, inshallah, from 3 to 5 September this year. We have the website, which I'm sure you've seen on the group, but anyway, I can send it again. And we're receiving applications. We are looking forward to this hackathon being a good experience for all the participants. We're planning to have teams that will work on different ideas, to have mentors, judges, and speakers, both from Egypt and outside of Egypt. So this series and the lab, of course, have been part of preparing the community and potential participants for this event. And we have more preparations coming up. And I'm sure there are many efforts in different institutions in Egypt as well. I know, for example, that Dr. Ahmed Yunus has a very strong program that he's preparing during the summer, and it's something that we're looking forward to. So with that, I think I'll leave it for the rest of our excellent speakers that we have today in order to allow them more time. And if any questions, please feel free to reach out. And I'm looking forward to it. Thank you all.
Thanks, Engineer Youssef. And Dr. Ahmed Yunus is going to talk about the unique programs that is going to start in Egypt soon in the presentation that we are going to see later today. And please take this opportunity because it's very unique to take a summer training from very distinguished people in quantum computing and quantum technology. Okay, so I'm going to just share my screen again. So the second speaker is Dr. Mohammed Zidan. He's an assistant professor in Bibliotheca University. He was supposed to talk about quantum machine learning and large data sets. Dr. Mohammed is attending with us now, but unfortunately he's sick. He got a strong cough, so he won't be able to speak. However, we are looking forward to his beautiful talk in next series. So please stay tuned to know more about quantum machine learning and how to quantify quantum machine learning advantage, and also how to apply it to the large data sets and to know more about the benchmarking and the state of the art in that field. So our next speaker is Malak Trabelsi Loeb. Malak is a very well-known speaker on quantum leadership and also consultancy in different unique technology disciplines and domains. So she's going to talk about quantum leadership and the space between disciplines. Let me briefly introduce her. So Malak is an international business jurist and also deep tech leader, forging legal and strategic pathways in quantum space and AI. She's also founder of Vernewell, or Vernewell in English. I just got the Dutch pronunciation of the words. Group. She drives deep tech management and strategy across the Middle East. As a CEO of Trabelsi Loeb legal consultancies, she crafts export control and compliance frameworks that turn frontier science into investable reality. Her high-level briefings and workshops to government agencies, NATO, and the Royal Aeronautical Society shape a responsible, future-ready technology adoption. So, yeah, welcome, Malak. Please feel free to share your presentation.
Thank you so much. Actually, I did not prepare a presentation. I would like to speak freely.
That's great.
The main points here for the presentation or for my talk is related to the initiatives related to quantum and AI and how it all started. This can be a way maybe for other leaders across the Middle East and North Africa or anywhere else to follow. And it is the most important part from the path that have been taken is it's not an orthodox path, which is not, so I'm not coming from the technological arena per se. So I'm not actually a quantum physicist or space engineer or AI developer, whatever is under AI. So my background is law and economics. That's my bachelor. And from there, it was going toward space, international space law. So my master was around space insurance contracts and how the space insurer filled the gaps when it comes to international laws and the issues that we've been seeing since the new space, and this is a word that it's a new space, which is different than the way how the space industry was before the revolution happening in the space industry. So actually, the path that the space industry, I see it, and I've took 1 year in stealth in order to study the space economy and the dynamics that it's within the new space economy, and I see a lot within the space industry. It's similar to the quantum in terms of the issues related to the national security, export control, the issues related to, when I say the national security, because there's a lot of implications of this technology on national security and vice versa. National security also has a big grip on the quantum technologies because there are some controls that needs to be done when it comes to hardware or software, and even brains. So actually, when you have educational or academics who are coming from different countries and entering into some of the projects that have like there are some secrecy in it, or even not secrecy, but it's the project. It's it has national security factors, or that you can learn something that you can take it and export that learning from your jurisdiction to another jurisdiction. This is what was the space industry before. So it's not about only the GPUs when we talk about AI. It's not only about, you know, the hardware. It's also about the software. It's also about the capacity who are working in this. And that was one of the, you know, the Eureka thing that happened when I was working on satellite technologies, and I still work on it. And I've seen the Chinese satellite that it was deployed in 2016. So it took my a lot of attention in order to understand the technology and what is the difference between the sat tech that we have at that time and the satellite technology that it is based on quantum communication. Whether it took me to trying to understand the physics, forget about it. It's not my thing, and I will never understand it. But the most important part is understanding, like, for example, what is QKD and what are the quantum post-quantum cryptography, what are the threats that we need to take care of and understand, what are the problems that these technology would bring to the surface. Also, when we talk about quantum sensing and stealth technologies, defense technologies, how they can be, you know, impacted by these kind of technologies. So since that time, it was like a loophole for me. No, it was a black hole, actually, when you enter into quantum and try to understand. And here, Dr. Ahmed Yunus is one of the respectable people I know personally who is working on this, and he's a professor well-versed in this arena. Actually, even for professors, when I talk to them, they tell me that it's a kind of a field that when you enter into it, you have always questions to try to solve. So it's not something that you stay there. Like, for example, if you are an aerospace engineer and you are a professor teaching this kind of technology or this kind of you know, discipline, you would be contented, or you see the type of new technologies that it is coming left and right in order to create more advanced technologies. But here it's science, and it's deep science, and it's never ending. So that's what I mean, that I would never understand that. And this is one of the things people, they claim they know quantum, who are not even having bachelor in quantum, or they are expert in quantum. And this I highlighted in some of the things. When I say quantum or AI or so forth, it's what is my background is legal, and I work on that. And there's one thing also I wanted to highlight. It's you do not need to be a quantum physicist in order to be in the quantum industry, and you do not need to be a technologist, like, for example, an engineer who is quantum engineer, because quantum engineer is a new thing, and you don't need to be that in order to work on different projects. And multidisciplinarity here and cross disciplines is very, very important in order to move forward. So here it's not to say again and to be misunderstood that you need to understand quantum physics in order to be there. And one thing in the beginning also, I saw the PQC people and the quantum communication guys who are working on real quantum, what they call it. They were not on the same path. They were not. It's like the first thing. No, he's not. And this, now you see that it's complementary to work together in order to move forward toward a safe, like quantum safe future. So going back to the point is moving forward in 2020 was the first company which was at that time Vernewell Quantum. It was Vernewell Space and Tech. And I started working with some with some consultants who are having a background of physics, and they were from the quantum industry. So I would not highlight the different other activities that I've done for nonprofit and others and groups. It's like hippie groups. They were very keen into moving the quantum science forward. But I'm talking about the venture that I created in order to move forward. And at 2020, when I started speaking to some entities in the region about quantum and the threat of quantum, and the first thing was, it's still not really our priority, because at that time, 2020, we did not have the breakthroughs in quantum computing that we see it today. So then all in the sudden is like, okay, sometimes I go back and say, but Malak, space is your thing, quantum is in the future, do not too much focus on this, because at the end of the day, most of the people, they tell you it's not going to happen. But it's the opposite. I kept on moving forward with that and creating small initiatives, were not knowing that much, and kept pushing forward the bar in order to move forward. And the most important part that I found is capacity building. That was something missing in the region. And the issue, even at that time, I wanted to have workshops, and the workshops, I needed to have some more workshop facilitators in UAE, and I couldn't find the right people in 2020 in order to do that, and it was online and so forth. So that was the most important part for me, is to bring forward. And so many of the workshops and others, a lot of my work, it's not publicized, because of course moving into publicity can also bring threats of you never know, hackers and others. So it's not about competition, it's the opposite, because more you do, the more you make people want to do the same thing. And this is one of the effects that it's known in innovation, because at certain point, cybersecurity industry, and I see William Slater is there. Hi, it's great to see you and meet you in person. Cybersecurity professional, they were not really happy about seeing quantum over there and taking the highlight because also it's a threat to their work. I mean, a cybersecurity professional, if he doesn't really know all the threats around and so forth, it's a problem. But some felt scared. The others felt that it's scared for their positions. The others is skeptical, and others, they don't want to hear or learn. But now, if you have a CISO and he's there in order to go to him and talk to him about the PQC and QKD, there is a big resistance, you know. But actually, regulations are there in order to move forward, and it's another question. So going back to the point, which was moving forward through capacity building, was one of the milestones that it was really important to make this, to move forward, because actually the initiatives that Vernewell started, it had a kind of dominoes effect across the region. And that was the biggest one, and people they are familiar with, was the 2024, the first Quantum Innovation Summit. And bringing together the ministries with the stakeholders who are from the industries, and industries, and I say it's plural, so it's not from the quantum industry only. We were very pushing forward to having the other industries, finance, I mean banking and finance, cybersecurity, and others, to understand exactly and to make the necessary awareness that the what we are talking about is not sci-fi, it's not far-fetched in the future. And I remember when I wanted to launch the 2024, and I was working on it on 2023 at that time. So again, it's not like all the what we've seen since end 2024 up to today. We're talking about end 2023 in UAE. And at that time, if you go and trace the activities happening, of course, you have the Technology Innovation Institute, the research arm of the Advanced Technology Council in Abu Dhabi, the entity leading the quantum technology in the region, and now they are also one of the biggest players of AI in the world with Falcon. And they have different models and in Arabic. So it's something that first in the world happening. So it's the moment of ChatGPT, with OpenAI. It's the moment for AI in Arabic, and so forth. And also they created their first spin-off, which is Quantum Gate. And this also the first time happened in the region to have from a research institute in the caliber of TII to have a spin-off, which is Quantum Gate, and it's specialized in post-quantum threat analysis and all the work that it is done on this is what I think. Of course, I'm not speaking on their behalf. They are the best to speak for themselves. But actually, I'm highlighting the company. They are creating or working on the sovereign cybersecurity like components that needed to be the initial steps going toward the implementation of the post-quantum cryptography. So the company was, I think, created in end 2024 or early 2025. I'm not sure exactly, but they are leading the way. And of course, we know very well in different countries, we need to have our sovereign entities to work on, things like cybersecurity and to access this data to move forward. So the Quantum Innovation Summit in between 2024 and 2025, we had the consortium Q Innovation, and we worked on the first challenge, which is not a hackathon, but a challenge. And that challenge was, it's before the, yes, I'm right. So the challenge is, it's not a hackathon. We approached different companies, leaders in this sectors. Thales was one, NVIDIA, IBM, who else? If I don't want to be NYU, so also it's academia to work on different problems. These problems are given by the leaders. So, for example, Thales, they had a problem for optimization of drone trajectory. So, we called for the challenge in order for researchers or universities and others to work on these challenges. And the thing that I was very, very proud of is to have also received a lot of applicants from the Arabic countries. And please do not, if you are in United States or in other countries in Europe or whatever, it's not a kind of bias, because we in the Arab countries, we are underrepresented in technologies, deep tech, like technologies like quantum. And when it comes to women, it's even worse. So we try to fill the gap and get our people to move forward. One of the biggest problem, I will tell you, to highlight, to have a visa and to go to another country in order to, for example, present in a conference. It's difficult in some for some researchers coming from countries like Egypt or Tunisia. The other thing is, like, for example, having a researcher want to go and move to another country in order to find better opportunities, because in some North African countries, the funding is very scarce, and maybe there is no funding for this kind of research. So better off for that person with a very good quality research or potential, actually, because if you don't have the means, we don't see the potential. We cannot see the potential. But of course, the professors, they see the potential. When I mentor a youth, I see the potential, and I say, if you are in another country, like for example in Germany or in United States or in Japan, you would do amazing job. So actually, the main point, also one of the main goals of the activities I've been doing, is to تمكين بالعربي تمكين العقول بالدول العربية. It's like to allow these brains to flourish and to move forward toward finding who they are, first of all, and what they want to do. And the Quantum Innovation Summit, it created this kind of forum, or maybe dynamic, in order to make this. And the challenge, I was really, really happy to see one of the groups who was the first winner. They were ladies from Saudi Arabia. So, and this one is like, really, I wasn't involved at all. I was so happy to have them. I wasn't involved at all in the solution. Of course, I mean, I could be involved in the business side of it, but I prefer to be not involved. So the jury could lead and take the over. So I did not know anything until they told me who are the winner. So the finalists, they've done, and the winners, they've done. I wasn't even aware, but they said it's amazing, because actually I was moving forward in order to push for more representation and calling people and reaching out on LinkedIn in order to get them involved. And I reached out to some lady from Saudi Arabia, and I asked her, can we meet? And when I talked to her, even without the camera or anything, I said, she's on fire. She's amazing. And her background is quantum computing. And she said that I'll see if there is possibility for biotechnology. So I told her, this is amazing. So she created a team, professor from a university in Saudi Arabia, King Fahd, I think, or King Abdulaziz, King Fahd, I think, I'm not sure. She was a professor, she's a professor in biotechnology. So they worked on DNA and DNA optimization, like optimization for a DNA solution to create a vaccine. And we had Merck Healthcare, Merck Health, or Merck, who was the company, the industry leader who provided this. And you know, Thomas Ehmer, He was in the judge also, so he followed up everything, and they had a great solution. So these are kind of activities that went on, and since the let's say before the 2025 in Feb, we started working on projects with industry and use cases, convince the industry within the UAE, arena, in order under the Q Innovation Consortium, in order to adopt. So we were working on adoption program and bring in the stakeholders who could, the adopter and the provider. And we work on project management basis in order to move forward. One of this project was announced during the summit, and now it's taken shape even bigger with the PR. It's the maritime, like the Abu Dhabi Maritime Academy is a part of Abu Dhabi Ports. And if you are familiar about Abu Dhabi Port, is a listed entity, and they are managing, I think, 17 ports worldwide, if I'm not mistaken. So, the announcement is to have ID Quantique to work on a quantum safe solution for their, like between ships. So, and of course, some of the trainings and others. This is one of the announced. We will be having a series of others, and we are working on use cases, which will be announced. There's something else also. We will have sector dedicated events in order to push forward the adoption of this because at the end of the day, in order to get these leaders to understand, they need to meet the people, and not in a setting of selling, okay, and not in the setting of I am here to sell you project, but rather it's we are here to work together toward the future by being a quantum enabled entity. And that's what we've been doing. So if you follow our work, you will know we will have also some series of workshops and initiatives with the Cybersecurity Council, which is the arm of the Abu Dhabi government cybersecurity. It's all UAE cybersecurity actually entity, and which was the host of the Quantum Innovation Summit 2025. And we continue to work together toward not only cybersecurity, but cybersecurity, quantum computing, and other technologies under the same umbrella to move forward with it.
Yeah.
I think I did not talk too much.
It's a very nice talk. Thank you very much, Malak, for this outstanding and nice talk. It's really inspiring. I see Dr. Ahmed. Yeah, please, Dr. Ahmed.
Yeah, actually, I'd like to thank Malak for not her talk, but her work. It was my pleasure to attend Quantum Innovation Summit 2025 with her. Actually, Malak is doing something. I work in quantum for more than 20 years. What she's doing, I believe it is impossible. But she made it possible. She gathered a lot of experts from different disciplinaries. She's actually forming the ecosystem in the Middle East, and in few years it will be in the world. Actually, one of her big achievement is the Quantum Future Forum. She gathered experts from science, from security experts, from governance, from she actually doing very, very, very excellent job. So it's really nice to meet you today, Malak.
Thank you so much. Thank you, Doctor. Thank you. And Dr. Ahmed, he participated in the Future Forum. Actually, it should be longer participation, but it's the first time, and it was a trial. Now we will be having. We are working on the white paper. Actually, it's not easy as I imagine that probably in 2 months they will be ready. But 5 working, like 5 white paper. and having different stakeholders involved, it takes time. So thank you so much for your words. And
Yeah,
actually all
actually,
that I do, it's because at the end of the day, my background is low. So I have my legal consultancy, and what I say, if I just sit and do contracts and practice, it's more fruitful for me. But actually, I do it for the love of bringing this kind of dynamic and see life change, and also move forward toward an achievable outcome, and not just for the talk. Because some people they see is like, wow, she's doing too much, or because they are not aware about the Quantum Innovation Summit this year. For the 3 days, we have around 1,000 people, which is more than the countries. They have a bigger ecosystem in it. So, and inshallah, next year it will be even bigger, and probably it will be in Abu Dhabi. I'm not sure yet, but we will see.
Thank you very much,
Thank you
Malak,
so much.
again for this nice and also the leadership inspired talk. As Dr. Ahmed said, you have been distinguished with many outstanding works to reform the ecosystem. Since you are not, you have other commitment and you will not be joining the Q&A session. So for technical questions, indeed, we are gonna forward to you later. But there is some question that's also shared by a major part of the audience about what is the most challenging task or work or thing you face as a leader Arab woman in this high-tech environment. What do you find is the challenging most?
First of all, being in UAE, I'm blessed because we are respected. And if there is, if I see, like, let's say, there is always unconscious biases, okay? If I see something that it's not appropriate, I speak up, and people, they know me that I'm not that type of person who doesn't. But being blessed to be in UAE, because it's like, as a woman doing business in the UAE, it's I mean, I think it's the best place you can be at in the Arabic world. This is number one. And this is not because I'm there or whatever, or I work in the UAE. I'm saying it straightforward. The second, okay, and don't hear or listen to what some of the social media or whatever that are saying is not true. There's a lot of competition, or others who are not saying the truth about what's happening. I'm there, you know, you go down, I go out sometimes. Not long ago, I went out because I wanted to pay something that I couldn't access through my gadgets. I went out to the gas station at 3 o'clock in the morning, and alone outside. I leave my my house door open and my car open. When I go down, nothing happened. I mean, where you can find that? This is number one. So it's important, the safety, and the safety of and the freedom of doing business is very, very important. Now I'm going to speak about women in technology in general. Okay, still there are some issues. For example, I don't have a background in tech. The problem is the people who have the background and they see my result. It's a problem with some who have that ego to see how she's done it and not me, or it's like it's a problem with some, and it get me in a situation where I get a little bit of harassment, you know. This is not only about it's irrelevant of being in the Middle East. It's generally, and I see this even in outside of the Middle East. The other point is to convince in the beginning that this is the right technology, and spending money, investing without having an ROI. And I tell you, I saw some others with what I went through, they wouldn't go forward to say that it's very difficult. It's like space, you know, it's very difficult and it's very hard, and there is no ROI. The ROI comes after. And so many things, it's like I've done, it's money put over there in that initiative, but there is no ROI at all. And I take it in a way that this is a part of the thing, and it's of what the result, it will not happen all over a night. and we should move forward in order to have so that was the difficulty, is to convince myself you are at the right place. This is the biggest difficulty. It's a challenge toward myself and not because of the others. They challenged me. So it's the other way around.
Yeah, thanks very much, Malak. We see the true inspiration and enthusiasm and energy. Thanks a lot, and thanks.
Thank you so much, and I will follow your talk later.
Yeah, indeed. Yeah, thanks very much again. Yeah.
Take care. Bye-bye.
Bye-bye.
Bye.
So now we are gonna move to the second speaker. Just allow me for a second to share the link. But before we go to the second speaker, I would like to thank quickly the team of the Quantum AI Lab. We have a monthly series of that's happening as a collaboration between Bibliotheca Alexandria and iQafé, and this is happening on monthly basis. However, we have also on weekly and sometimes on bi-weekly basis to avoid vacations and the national holidays in different places. We have also Quantum AI Lab that's done and organized in Arabic, and I would like to thank the team that's organizing and giving either lectures or codes or notebooks or explanations. In particular, Ahmed Saad Al-Fi'i, he's a distinguished researcher in quantum computing, and Gamal Munib is also an engineer, a distinguished engineer in programming and AI arena. Okay, so our upcoming speaker is a very unique one. So Clark Alexander, he's gonna talk about a very important topic: why artificial general intelligence or ASI and gate-based quantum computing limited from energy side. Why they are limited from energy side. And this is very important because now we expect that we can scale forever the kind of AI models, or this is the main hope, not expectations. But Dr. Clark is gonna highlight this. So before he starts, I would like to briefly introduce Dr. Clark. So he's a co-founder of a company, Enerjuice, a renewable energy IP firm. He's also co-founder of Open Plugory Network. Plugory Network, a non-profit data and energy training company. He's also advisor at NETL, Mathematics and Physics in Data Processing, advisor of ODEL3C, a quantum computational chemistry company. He has multiple roles at Batch Freight, head of AI, SR, director of engineering, and the head of research and development. He's also commissioner at ISO region 735. He has 50 plus citations in quantum computing and mathematical physics. He's also lectured for 10 years in 5 universities. And of course, the beautiful thing is amateur music composer and polyglot wannabe. Okay, welcome, Clark. Please, the floor is yours.
Thank you very much. I'd like to speak about soccer and putting teams together all day long, and why soccer is the correct word, but we'll skip that. I want to start maybe with a little thought experiment. And here's my question. You can think about this as we're talking. Like, how tall a tower could you build out of Legos? What's the maximum height you could build out of Legos? Just using Legos, no glue, no glue. What's the tallest tower, right? And so the answer is there's two answers to this. Mathematically, as much as you want, but physically there's some limit, right? And the important thing to get out of this question, you can think about it as we go. The important thing to think about is at this scale, there are physical barriers, right? There's a big energy consumption in like building the towers up. And so I'm talking about massive energy, tiny energy. And so in this case, what we have is artificial intelligence is limited by massive energy. Quantum computing is limited by minute energy, okay? And so I think one of the things that we don't think about, I like what Malak said, you don't have to be a quantum physicist to be in the quantum computing ecosphere, but you should probably know it to develop algorithms, and probably in the engineering side of it. So here's the idea, right? Artificial intelligence. what we've seen in the last year, so I looked this up, CO2, CO2.earth had a really good write-up yesterday. So Sunday, this few days ago, the parts per million of CO2 in the atmosphere was 430.15. Okay, we're trying to limit it to 350, so we're 23% over. Okay, a year ago, May 25th, was 426. So we've added 4 parts per million of CO2 in the last year. So the question is, how did we do this? And the answer is, let's take in all the really, really carbon intensive applications and see what increased. There's world travel, there's all the logistics stuff, there's production of EVs and production of renewable energies, and then there's AI. And I think if you go through all of these things, you'll find that the only one that's really increased that much or more is the AI. Okay, so ChatGPT, is probably the biggest offender. They're not the only offender, but ChatGPT is contributing to like a massive amount of CO2 emissions, right? And part of it is that it's not really engineered for efficiency. It's engineered for use, right? But at a modern industrial scale, energy has to be one of the considerations. So teaching for many years at university, when I was teaching algorithmic analysis, we talk about speed and memory usage, right? And there's always some sort of trade-off between speed and memory. You could store more stuff in memory to get a faster algorithm. You could run a faster algorithm if you forgo the memory, okay? Now in modern computing, like energy use is that third resource. It really counts. The energy use really, 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 really counts. And I'll tell you, I talked to Oak Ridge National Lab, which is funded by the Department of Energy of the United States. When they were building their Frontier supercomputer, which has recently been clocked as the most efficient, most number of computations per kilowatt hour that has ever been built, they told me the reason they didn't build a twice as big computer is because they couldn't afford the electricity bill. And they work for the Department of Energy. I mean, like, we're talking about big players here. We're not talking about small time work on your little laptop, do your home projects. That's not what we're talking about. We're talking about a massive scale. Now, let's extend this to AI. ChatGPT is asking for opening a new nuclear facility or reopening a nuclear facility, right? The amount of energy that this needs, well, basically you should say you should have engineered this better, right? This is unsustainable. We're just going to fry the whole planet for the sake of everyone getting a chatbot. So like, maybe think about that, okay? Now, the other problem is this, right? Artificial general intelligence, we want to think that, well, I mean, what does this mean? It means that we have some computer that's able to perform like all the tasks that we need performed at a human level or better. But I want to pose it in this way. To get like super intelligence, I would like for a computer to be able to do this more efficiently than a human. That's what it means to me in super intelligence. So I love chess engines. Let's talk about chess engines for a minute. I'm not a very good chess player. I'm not very good. I've played a few hundred games of chess and have been beaten by a lot of good players. I'm not very good. But the modern chess engines, like let's say Stockfish, Houdini, AlphaZero, they have memorized like terabytes of data. Terabytes, right? That's way more than any human could ever play just in memory. Okay, can a chess engine beat me, a not very good player, having played only like a few hundred games with less energy consumption? Because the answer is definitely not never. There's no chance. No chance it could ever do this. Our brains are like so energy efficient. We've developed this way. Okay, so that's one thing. Artificial superintelligence will mean that we'll be able to have a computer which is able to outperform a human with less energy. Before this, it's just pouring more and more and more energy into the problem. Now, from an information theoretic perspective, if you've ever gone through this exercise of doing the thermodynamics and energy calculations, you'll find that the distance in information space is like a hyperbolic distance, right? Which means bring it simply down. If you want to constrain the variation and you want something to be like really exact, it costs infinitely more energy. The closer you get to zero variation, it costs infinitely more energy, right? And so like this marginal returns really hits. In an AI space, that's reducing hallucinations. To reduce the hallucinations down to zero, we will never, ever be able to produce enough energy to do that. It is not physically possible. There is a barrier, and that's why I asked the question about building a Lego tower. How tall can you build it? There's a physical constraint to how tall you can build it, not a mathematical one. Mathematically, it's possible to reduce hallucinations down to zero, but physically, it is not. Right, so artificial superintelligence, not in the current structure we have. We have to have a complete rethinking of how this works. Okay, now, that's the constraint on like the large side, like way over here. How much energy do we have? How much can we get? Let's now go down to quantum computing. There's on the other end of the scale, there's a reason. Astro movie, you're killing me. It's boiling the ocean vibe coding. Okay, actually physically boiling the ocean. All right, so on quantum computing, IBM recently with a German company on their 156 qubit processor performed like an optimization that I think they scaled it against simulated annealing, which makes me happy. This is my expertise. But I think it came in at like 30 times faster for a better quality solution. And so a lot of times in quantum computing, we're hearing about energy saying, oh, the energy in the computation is so much more efficient. And what this ignores completely is the overhead of getting things started. So look this up. IBM, in their literature, say this is a 25 kilowatt refrigerator, which they have to cool for 4 days to get it down to processing speed. Okay, so that's 2.4 megawatt hours. My question to you is, how much computation on a digital computer could you get done for 2.4 megawatt hours of electricity? The answer is like everything in the whole world. Like you can compute weather on this, right? It takes less energy to compute weather patterns across the world than that. So is it worth it to wait 4 days for one optimization? Or could I just run it on my laptop for 1/30th of the time and get a really close or good solution with like this much energy? So, right, we have to make this balance. Hany, go for it.
Yeah, Hany, please.
I do have a question. Maybe another argument is maybe it's just things are just getting started and you have a few number of qubits that maybe it's comparable to solve by classical computers, but maybe in the future it's going to be a lot more. I mean, the barrier between what you can solve with quantum versus classical will be a lot larger, that you cannot even compute something, even if you take the end of the word to solve it on classical computers. Maybe it's
Exactly
just
right.
inefficiencies at the beginning, and it will be better in the future.
Yes, perfect. It's like I didn't pay Hany. I promise I didn't pay him. He's set me up perfectly. So rock and roll. The question now becomes, you know, if we can solve something that's like so much better, fine, perfect. Then all that overhead electricity is not going to count. Right? It's just like you have some starting point and it's just an affine transformation and fine, whatever. The question is, like, for most industrial applications, what I'm working on now is an optimization problem in this. And the question is, what's the second best or third best or fourth best or fifth best or sixth best option? What happens if you're doing this optimization problem and a factory in South Korea goes on strike? You need a solution right now and you don't have the 4 days to do it. Well, I mean, you have to set it back up, okay? But the other problem with modern optimization techniques, I've talked to a bunch of guys, and they're saying, well, we want the best possible solution. And it's like, in reality, that's never the case, right? Like in stock trading, something I've done several times, building optimal portfolios, there's too many possibilities. Maybe you can't get the best one. Maybe some of the options are not shortable. You can't borrow the stock. Okay, so we need a good enough solution quickly before the prices change on us, before the factory goes on strike, before we have to lose our contract. Okay, classical computing can do this. Now, The other really interesting thing about classical computing is there's been this arms race. I've been saying this since 2019. There are a bunch of probabilistic programmers that are like trying to push quantum supremacy back and back and back and back. They keep getting more and more clever algorithms, which they can run probabilistically, getting better first guesses, adaptive solutions, using quantum-inspired techniques, right? But it's not actually quantum hardware, it's quantum-inspired techniques that are pushing back the quantum hardware further and further. Okay, so let's ask this question. What is quantum supremacy and what is quantum advantage? What does that mean? I think we didn't define this well. But I want to put this definition forward.
Yeah, the definitions also is quite changing from time to time. Yeah, Dr. Ahmed, please.
Ahmed.
Actually, I agree with you in terms of the current technology we have. But if we ask that question a long time ago when they invented cars, and we have horses, and the horse consume less energy than cars, and it was faster than cars at that time. If we decide that cars will not do the job, we will not reach to the level we have now. So we have technological side and a theoretical side. Theoretical side promise that actually we can solve problem much faster using quantum technology, but the current technology did not achieve this. So we cannot take that decision based on the current technology. That's only my comment.
That's fair. So let's ask what is quantum supremacy? Now let's check this.
Okay,
Here's my-
can I answer this? Quantum advantage is we can do things using quantum much faster than or better than we can do on classical computer. So this is a quantum advantage. Quantum supremacy means we can solve problems that it cannot be solved using classical computer. So quantum advantage we can do using classical computer, but we can do it better using quantum computer. Quantum supremacy, we can achieve something we cannot do using classical computer. This is a simple definition, I believe.
I will agree with you on advantage, but I would like to put it this way. Quantum advantage means that there is a quantum hardware that can perform at least one task in at least one of the resources that we pay attention to faster or better. That's speed or energy consumption or memory and space. One of those things has to be better in a quantum computer. And I think we've achieved this, right? I think Morgan Chase did a good job with certified randomness. So I think advantage has been achieved. Now, supremacy for me is like all three of those things have to be beat for all problems. Any supercomputer cannot perform what a quantum computer can do on the amount of energy, the amount of space, or the time.
Yeah, so
I think that's what supremacy means.
Okay, so we have a comment or question from Jan. Jan, please.
Yeah. My comment is I basically agree with what has been discussed. I would like to add the concept of a useful business problem. Yeah. So not only a theoretical thing, yeah, but a useful business problem, which can be a scientific research thing, which can be some medicine, some molecule that needs to be calculated. Yeah. And also, I would like to add, basically react to what Dr. Alexander said first. We will need at least a factor 1,000 improvement in energy efficiency in classical hardware. Yeah. Otherwise, it will be not feasible to do any training of machine ML models. Yeah. I mean, you can do it if everything is free, but nothing is free. We should know that. Yeah? So if we want to really deploy AI, machine learning in combination with quantum computing, the cost really must go down. Yeah.
Yeah.
And I will show later on in my small talk, I will show some numbers, which I hope encourages you. So
Yeah. So
Yeah. I mean, some stuff has to happen. I'll finish just with one final. I guess there's two pieces I wanted to talk about. In quantum computing, why Q-Day? Q-Day is this day, supposed day when RSA will be broken by a quantum computer. That will never happen. That's just not physically possible, and here's why. On quantum Fourier transform, right? The quantum Fourier transform, as currently written, relies on rotations of qubits, of angles of pi over 2 to the n.
mm-hmm.
Right? So if you're looking at like a 156 qubit processor, half of the register is the thing, and the other is the ancillary qubits. So we're looking at a rotation of 2 to the 78. All right, so pi over 2 to the 78, that's 10 to the minus 53. That's 0. That's 0. Okay, but more importantly, the uncertainty limit gets us down to about 10 to the minus 16 electron volt seconds. The rotation you need to factor something with a quantum Fourier transform is so far beyond the limit of uncertainty that it just is not, it's not physically possible. There's a barrier down there. It's not like I don't want that to happen, it's that it can't. Right? This is like, how tiny can you build a Lego tower? Right? There's a limit. It's the smallest Lego. There's no smaller Lego than that. Right? You can't build a tower less than that. And so there's this physical barrier on quantum Fourier transforms. That's the other problem. I'm not saying it can't be done. I'm saying that it can't be done with quantum Fourier transforms. We have to have a complete rethinking algorithmically before that can actually happen. Right? But even Peter Sarnak, he's one of our preeminent number theorists, he doesn't think that fast factoring is even an issue. I mean, back in 2010, I drove him around to the airport from a talk he gave. He said, I'll just throw in fast factoring. That's going to happen. He was extremely dismissive, and his talk was about quantum gates and their topology. And he was like, fast factoring is a thing. That's not interesting. So quantum Fourier transforms ain't going to do it. Something else has to do it. Because there's an uncertainty limit, and we can't get like 27 orders of magnitude better than that. That's just not how physics works. So, weird thing about our universe. Last thing, going back to the AI, my business partner with Open Plugory Networks on here, I think. We have launched recently, this is around AIs, we've launched the International Declaration of Data Sovereignty. And for us, like the amount of training that large language models are using is like, it's too much. And the other ethical piece is that, for the Europeans, this makes more sense. It's your data, you should be able to control it. Right? The large language models are taking all your data and just selling it off without giving the content creators anything. So we reimagined this and said, well, what happens if you just use Wikipedia and had a search engine and then allowed the content creators to send their data willingly, right? So we only get your data if you give it to us, right? So what we're trying to do is collect 1 million signatures on this Declaration of Data Sovereignty. I'll send you the link and you can send it out to people. It costs $0. It's just a signature saying that we think this is how AI should be done going forward. I'll take plenty of questions on that later, but that's all I had to say for today. Sorry, I went on a little longer than I had anticipated, but
yeah, thanks, Clark, very much for
yeah,
thanks very much. It's very interesting. Also a thought. I've been working myself on an episode for the YouTube channel about how time is limiting, also from the concept of time limiting also, and putting theoretical limits on the ability to do quantum computations, because sometimes we ignore a lot of things related to how to increase the coherence time, and also how the uncertainty principles, but also the theoretical laws of thermodynamics puts upper limit on that we might hit a wall with the scalability of qubits. But of course, this is the main theory. We will hit it much shorter because of the engineering problems, but this is the highest theoretical limits that even touches sometimes the fabric of space time.
Which
so
means that we would need an algorithmic rethinking. It's not that we can't factor quickly, it's that we can't do it with quantum Fourier transform because of this thermodynamic limit. It's not that like it's not possible. It's not possible in this way. We have to be very, very, very clear what we're saying. I'm not saying like, nope, just give up, go home. I'm saying like this will hit a limit, and it's sooner than we're ready for. And that's kind of why I think quantum mechanics needs to be taught for the algorithmic developers a little sooner than after they've started their job.
Yeah, that's really great, and also that also source of inspiration for research on this arena. So we have two questions. The first one from Karim Safti. Please go ahead, Karim.
Hi, can you hear me?
Yes.
Yeah, great. Thanks a lot for like this session and everything. My question is regarding AI specifically in training, much more specifically for quantization aware training. Like, let's say instead of using float 32 for like data representation, let's say that we went to like integer 16 or integer 8. I know that the accuracy will go down a little bit, but regarding energy consumption and like preserving a little bit of the energy cost, or like reducing the energy cost, would that be good on the short term, or like in the near future, or
actually, I sent a draft of this talk to Taha, and like that's half of the paper. Using less decimal places, because here's the point, right?
Oh, okay.
So,
I didn't know that.
Yeah, let me give you like some actual real world stuff that I've dealt with in the last 2 weeks. I'm working with a supply chain optimization problem, and we have 7 million parameters. Okay, but we're calculating things to the closest dollar. So I told my team, don't save anything past 8 decimal places. And they're like, why? It's like, because it won't affect it even $1. And then the contract gets negotiated anyway. You could give it to the nearest $10, cut off 6 decimal places, and it cannot possibly change the final result out of 7 million, right? This is a binary optimization. So you add them all up, that 6 decimal place can give you up to, $1. In this case, it was $7, right? The same thing, we saw this with DeepSeek, right? DeepSeek came and stored float 16s or even float 8s, I think, and it came faster. And the point is that there's a lot of data and a lot of energy spent storing just those extra decimal places, which do not affect the final result. And probabilistically, I mean, we don't need the 16th decimal place. We just do not. We just don't. I mean, I run Julia for most of my computing, and half of my result is I just round it. I round it to like 3 decimal places. Just throw away everything so I can store it, and I can send like a lot more data to my team, like, because it's a lot cheaper. I mean, float 8 is where I want to go, or M16. Yeah, absolutely. It's a huge energy cost just to store all that extra data and do all the computations on the decimal places, which make literally 0 difference in the final result. 0, not like 10 to the minus 0.
It's good that you mentioned this.
Words in English or in French. Like, if you're that many decimal places, probabilistically, you're not going to get any more difference after that.
Yeah,
right?
so that's a great point that you tell about that difference, because also in chemistry, we sometimes test this sensitivity if how many digits, after how many digits this would affect the final results. For example, and we achieve, for example, up to the 10th or so, 10 digits, and then after that is it's basically only for numerical comparison if we make a use case in testing the software. So we have a question from, please.
The other easy thing is to stop using Python, because Python's like 40 times more energy intensive than Java or C++ or Julia or Scala. Like Netflix uses Scala for like exactly this reason, right? They don't use all the decimal places, and they use Scala because they need the big data problem, they need it fast, and they're incentivized literally any other language than Python. F#, C#, Go, Scala, Java, C++, Rust. I mean, I can go on all day. Python is like the most energy intensive one. So let's just put some parameters here. ChatGPT uses Python and all the decimal places, right? Use C#, store only a few decimal places like Karim says, you're 120x energy more efficient, 120 times more energy efficient for the same result.
Yeah, this is what I wanted to hear, specifically like the number of, the difference itself, because like
now, if you can only put on
solutions and stuff
you
like
save
that,
yourself
like
another few orders of magnitude. Yeah, you can get way, way, way down in energy cost for a nearly identical result.
So for more information, we have done a podcast. Of course, I don't want to enforce my own bias, but I will make it implicit. I'm also using Julia and all my simulators for quantum computing and the chemistry, but I'm not gonna criticize any other platform. But yeah, just you can hear the criticism in our podcast, Clark and I. I'm gonna post the link later from the YouTube channel where for 2 hours, all of these details have been discussed extensively. So please feel free to watch it and comment on it.
Here's something. I'm really sorry. I have one more question, like specifically in Python. If you are using like a platform like JAX, and like the first iteration in any training will take some time for the compilation, but right after that, all your code is basically machine code, and you can run in like basically machine code. It's super fast. It's even faster than PyTorch and TensorFlow. So from a computation point of view and energy point of view, do you agree that might be beneficial for like fast prototyping or even production level using JAX itself? Or have you tried something like this? Or
I haven't used JAX, but my understanding is that it's about 20x energy efficiency in Python. That's my understanding, and this is by people who have clocked it, not myself. So, you know, I'd take 20x energy improvement. I'd take that all day.
Mm-hmm. Okay. Thank you.
I'd take that to the bank and I'd ask investors for it. I mean, I would literally take that. I think we're sleeping a little bit on the .NET platform and Julia and Rust, but you know, I'm not super language focused, except not Python.
Rust is great, but the community support is not that great, you know. True. But I mean, here's the question: how much energy does it take to teach enough people to learn this versus how much energy Python is using for people who didn't bother to learn the mathematics? Now, Python's a gluing language. It's a teaching language. It's not an AI language proper. It became an AI language because people learned it. It's easy to learn, and they started building packages into it. It was not built for that. Python was built as a teaching language, right? Scala is built as a data language, for example. And have you tried like using FPGAs at the very end, like in during the deployment itself? Have you tried FPGAs? Like after training everything and just deploying it?
I don't know if you hear me or not, because I don't see the signal, but please go, Hany, for your question.
Oh, sorry.
Yes.
Sorry.
Yeah. Well, I get the flavor of what you are trying to say, that energy is important to take into account, not just the computational power or the speed that a technology that promises. But quantum, well, especially quantum computing, which is my area of expertise, is a bit undefined industry at the moment. And currently all the resources brought in, they do not think about energy consumption or cost or something, which I don't think it's a good thing, but it's yet to be, the potential is yet to be unlocked because we don't know where is that going to be. So it's a bit, I don't want to say dismissive, but like it's not yet optimized to run like on daily basis in order to optimize energy consumption. It's actually funny that actually the Google team just published a paper a week ago that saying that they previously anticipated they need 20 billion qubits and they need some error rates that is very good, like below 10 to minus 3 to break the like to do the factorization problem large enough that they can be you know, broken by a large enough quantum computer. And this last week they anticipated they only need 1 million with the current improvement of error rates with the last processor. So it's I want to say it's just a moving field. If there was no potential at all, why would big companies invest in all in quantum computing, right? There is a lot of potential and the field is moving. So having assumptions based on the current state may not be fair for the potential of where this is can go. That's what I want to say.
Yeah. My question is, can you entangle 1 million qubits? I don't think that's even been settled.
Yeah, indeed.
I think entangling 1 million qubits fully entangled is beyond uncertainty limit. That's my take, right? There's an energy barrier down there, and I think literally no one's talking about it because it doesn't force investments. If I'm a company, right? If I'm Google and I say, we can get this down to 1 million qubits. Am I going to go tell my investor that 1 million qubits is not possible? Oh, hell no, I would never do that. I would never, ever say such a thing. I'll be like, we can break all the security.
If they know that is not going to happen, why would they do it? I mean, they are large enough that they have money. They are actually investing a lot of money themselves in building this technology. It's not like they are gaining money yet from this technology. Why would they even invest if they see no reason to?
This is my assumption, right? I don't work for Google and I'm not getting paid by them or against them. Whenever you're a research scientist, so you start trying to solve a problem and then some other problem comes up and you see some utility that you didn't expect before, right? So, I studied random matrices, and then the first thing I did when I became a data scientist was I used random matrices to detect corruption in data sets. I didn't know that was going to happen. That's not why I started studying random matrices. It just turned out that that was a thing. Right, I suspect that we're going to see a lot of quantum advantage come out of particular algorithms, right? The thing that's going to drive investment and drive journalists and get people like excited about quantum computing is, oh, we can break the banking system and we can steal all the money back from the rich guys or some bullshit like this, right? Whatever it is. I don't think that's the goal. I think the goal is to find the algorithms that actually give some advantage industrially with hardware that can be done. I mean, I think that there are a couple of companies that are actually trying to build for specific modern hardware, and they're trying to build advantage. My argument is that quantum supremacy is very, very, very unlikely. Quantum advantage is extremely likely, but it's probably not where we expect it to happen. And that's what I think a lot of impetus of the investment coming in is, it's a solution looking for a problem. What's the thing that's going to give us quantum advantage? Probably not the thing that we expect right now. But if we don't put the money, we're not going to find it at all.
Yeah, so that's
right? It's that kind of gamble. That's my take on it, and I could be wrong. I could be completely wrong, but I don't think they're soliciting journalist articles and money for actually breaking RSA. I don't think that's physically going to happen. I think they're going to find something else, and then they can make the big, oh, Google scientists discovered advantage in solving a logistical, whatever. Right.
Well, I agree with that. I agree with that. Like there is a hype behind gaining or having money invested in quantum and convincing investors that they should invest in quantum because there is a problem that is not far away and it has a lot of potential and so on. I agree with that, but the other part that it has no advantage at all, it could achieve no supremacy. I found it very hard to tell from now because we don't know where is it going to be. I mean, nobody knows. That's the true answer to it. But it has a potential that we shouldn't stop. That's what I mean.
Yeah, so let's take these two interesting lines indeed further in the discussion, and we see now what is the hardware, what's happening from the hardware side with Dr. Hany Ali, and then we see, okay, how far, where is the progress of quantum computing at the moment. I'm just sharing the screen quickly.
Thanks, and I apologize for taking more time than was allotted to me. So
no, thanks, Clark, very much for your nice talk and nice presentation. I think I lost my sound, so you didn't hear. I found that when I was checking the signal. Thanks a lot for this interesting thought, because it's all the time we need to think about the reality of what's actually happening. I mean, apart from interesting, presumably seductive points in science that might lead to good proposals, but then we come to the discussion about the commercial advantage, and then what could now my mic is working. So thanks very much for your interesting talk. And now we are gonna move to this talk also. Thanks, Clark, again for a very nice talk. And hopefully we are doing a podcast and also in the book that we potentially would like to publish later, we highlight this issue in more detail. So our upcoming speaker is, of course, Dr. Hany Ali, and he's gonna talk about his PhD work that has been defended recently, a distant 3 superconducting surface code from calibration to logical performance. a short bio. So Hany Ali is a senior measurement engineer at Quantware. It's a startup in Delft. He holds a bachelor degree in science in electrical engineering from Suez Canal University and a master of science in microelectronics from ESIEE in Paris, and conducted his master's thesis at IMEC in Louvain, focusing on thin film transistors. His expertise extends to quantum computing, where he pursued his PhD in quantum error correction with transmon qubits at Di Carlo Lab, QTech, starting in 2019. His PhD thesis is titled Surface Superconducting Quantum Processors from Calibration to Logical Performance. Driven by the ambition to build a powerful computer, he of course has his career path, and that career path evolved from electrical engineering to thin film electronics, and now to practical quantum computing. And he has many outstanding habits and hobby as well. Like, he's socially active and enjoys cooking, music, movies, and football. Nothing better than having a good cooked meal from experimental physicist, where everything is on precise in the recipe. Yeah, the floor is yours, Dr. Hany. Please go ahead.
Yeah, thank you, everyone. Let me share the screen first and confirm that you see the screen and you see the laser beam. The pointer. Okay, let me first. Okay, can you confirm what you do? You see the presentation mode? Yeah. Okay. And then yeah, and you see the laser pointer, right? Yeah.
Yes.
So let's get started. Hello, everyone. Nice to meet all of you today. I'm very excited to talk about my work during the PhD and maybe after the PhD as well. The talk title is Superconducting Surface Code from Calibration to Logical Performance. So it's really technical, and there are so many technical keywords here that I will try to have less technical level, so for general audience to grasp what I want to say. But sometimes you will see some technical terms, or if you see something that is not very clear, so please interrupt me and ask questions. Okay, so I would like to answer the question, what is it that I do? And also for general audience to grasp what is a quantum computer, what is the potential of quantum computer, and is it visible? Is it useful? I mean, this also reflects on the previous discussion with Dr. Clark. Okay. From the history of computation, when humans thought, okay, we need to have and solve certain problems, so we invented the math rules, and we could do some math, maybe up to a few, maybe a few tens or hundreds of math problems that we can solve. But soon we realized that we cannot solve a lot of problems that have some, some relevance to real life. And actually, from the 16th century and even until now, there are a lot of technological inventions that came to solve computational problems, just to perform computation from all the 16th century. I will actually like to focus only on the last maybe 50 years, 100 years, where really the technology becomes or revolutionize what we are today. Actually, believe it or not, that what is in our hands is a very smart computer. The smartphone is a very good computer that we imagined we won't have maybe 50 years ago. 50 years ago, the computer had a very big room with all the vacuum tubes and so on, and it evolved with the semiconductor industry all the way to supercomputers right now. And this begs the question, what's next? Many people believe that the next technology will be quantum or will be based on quantum. Yes, you heard right. Probably quantum is something that you heard of during your high school. It's actually a mathematical framework to explain how atoms work and to explain interactions happen at the atomic scale. This quantum computer uses some quantum mechanics phenomena that actually governs the atoms and how atoms interact together in order to perform computation. This is as an opposite to classical computers where you often see this zeros and ones where information can only be encoded in these digits. So this is like a new paradigm that uses quantum mechanics phenomena in order to perform computation. So this is what we call a quantum computer. Okay, here is a quick comparison and probably a very simple comparison between classical and quantum computers. So the basic unit, or I would say the encoding paradigm for quantum computer versus classical computer is entirely different. So for classical computer, as I said, the information can be encoded only in digits, either zeros or ones. While in quantum, you often see this sphere, what we call the block sphere. This encodes information differently. Information can be encoded in zeros, ones, or combinations between zeros and ones. I will come to this point later on. For the physical system, classical computers consist of transistors, which we know very well by now. Quantum computers can consist of various physical platforms, including superconducting qubits, ion traps, quantum dots, neutral atoms, photonics, and so on. There are so many physical platforms that can actually perform as a computer based on quantum mechanics phenomena. What is really striking for the difference between classical and quantum computer is really the error rate, is how well we do computation, how many computations we do before we find an error, before we have an error, right? So for classical computer, the error rate is 10 to minus 13 to 10 to minus 18. This is quite very small error. So before we perform, like say 10 trillion computations, we have an error, which means that this is a very, very reliable computer, right? For quantum computer, it's not the case. For quantum computer, we really have a lot of errors, and the error rate is at best 10 to minus 2 to 10 to minus 4. That's the best error rate we can get. So,
Robin,
sure?
box delivered.
Is there a question?
No, I think
Okay.
so, yeah, please go ahead.
Yeah. Okay. So that means that every 100 computation, there is an error. Every 10,000 computation, at best, there is an error. I mean, you may say, okay, this is useless, right? If you are a computer scientist or come from different background, you say, why do we even talk about this? Because the error rate is just huge, right? We cannot do anything useful with quantum, but there is a catch to that. So I will tell you more in the coming slides. So the source of errors, I mean, in classical, as I said, it's very rare. That comes from the clock jitter or from the background radiation, which is really, really rare. It rarely happens. In quantum computer, it's different because quantum has a lot of degrees of freedom than the classical computer has. So they also introduce a lot of errors coming from temperature variations, mechanical fluctuation, microwave noise, and electromagnetic field around as well. So all of these can be a source for error and can explain why this error rate is quite high. For classical computer, even the error is so rare to happen. We want to correct also for this error to perform better, like more computation. And for that, what we do is we create a copy of the state that we want. We create, like say, 3 copies, and if there is an error, that happens to one of the copies, you can still retrieve the good computation by taking the majority voting. This is called the majority voting. But since the error is like very, very rare to happen, so it means that this majority voting will still be an efficient way to correct for errors because errors happen rarely. So that's an efficient way for classical computers to work. For quantum, it's a bit different. So since we have a very noisy qubits, the physical performance is quite bad. As I said, what we do is we create so many copies of the state that we want in a framework. This framework creates like the many copies, introduces redundancy all over your algorithm. So if an error happens there or here around the physical qubits, the effective state that you want to protect or you want to encode still has a low enough error rate, or still you can still detect that an error happens in this qubit or that qubit. So the idea is to create so many copies, not just 3 or 4, is you need to create so many copies of the state that you want. And even if you lose some of it over the course of computations, you can still retrieve the good state. So it means that you are trying to create, like it's like the keys. You want to have keys everywhere, that you don't want to lose this key. So even if you lose it somewhere, you still have other sources to tell you what is the key or what is the information you're trying to encode. Okay, any questions so far? All right. A big difference between quantum and classical computers is the encoding. How do we encode information? So this is an example of why quantum computers could be better. In classical computers, if you think about the space where you encode information, you can only encode information in zeros and ones, right? It's either the North Pole or the South Pole if you imagine a sphere. In quantum computers, thanks to quantum superposition, the states can be in any superposition of zeros and ones, can have probabilities to stay between zeros and ones. So the analogy here is you can only use 2 points on the surface of the sphere, while in quantum you can use any point on the sphere to encode information. So that's plus the quantum entanglement and quantum interference. This gives a boost to quantum computers to explore vast solution space in parallel, because the computational power for what you can encode information in is quite large with respect to what you have in classical computers. So this is why quantum could be better, because it explores a lot of parameter space in parallel, and that gives an advantage in computational power. So classical computers are quite amazing. We all know by now that it changed the world, right? Since we have now supercomputers and even powered by AI and so on, this will even change the world further. But classical computers have a lot of problems to solve, certain type of problems that scale up exponentially with size. So any problem that requires exponential computational resources in size, classical computers will have hard time to solve. And one of these famous problems is factorization problem, as we discussed early in the previous talk. This is a backbone for any encryption protocol at the moment. And Peter Shor, who is a distinguished scientist in 1994, he actually came up with an algorithm to break, to solve the factorization problem for using large enough quantum computer, and this can break a lot of encryption protocols that we use today in communication and commerce. The second problem, and probably to me this is a more interesting problem. Maybe the first problem is like a punchline to get more funds and so on, to get people more afraid of quantum computer and to kind of stimulate the national security concerns, probably. The second problem is even more interesting, which is about Richard Feynman, who actually proposed the idea, is if we have molecular geometry, or if we have molecular interaction between multiple molecules, the degrees of freedom in this problem is quite large and scales up with the number of molecules and also the degrees of freedom for each molecule. So that takes a lot of time for classical computers to solve, and they cannot even solve it with a good uncertainty. So that's why, for example, the drug discovery and the protocols to have a good and new medicine takes a lot of effort and years of trials in order to reach the good medicine that is thoroughly tested. With quantum computer can naturally simulate the molecule interactions because they follow the same Schrödinger equation or the same Hamiltonian as these molecules do. And therefore, the hope is to use quantum computer to actually simulate chemical interactions for the drug delivery. I mean, if this works, this can be a potential or large potential to discover drugs and to actually perform simulations for molecules without even doing all the, all the technological, the hard work that we do now, because we don't have a good enough system to simulate these molecules, how they work together. The third one is searching through unsorted data. I mean, this is a technical term, but you can think of it as, for example, how do we solve traffic control, right? If we have a lot of traffic and if we have roads, and how do we solve the traffic control, given that there are a lot of inputs, and these inputs can grow exponentially? How do we solve such a problem? Is quite hard by classical computers at the moment, and they limit their computational power. They explode quite quickly when you give a lot of inputs to these kind of problems. So any optimization problem, this can apply to anything. Any optimization problem that is quite complex, classical computers have hard time to simulate, and the promise for quantum computers to be able to solve these much faster, because they can explore a lot of parameter space in parallel. And of course, there are many more applications that we even don't know yet, because it's a quite moving field and it's just getting started. One of the famous things is AI, and everyone is saying AI as a way to, as a keyword to get attention these days. But AI can both use and power quantum computers. So, for example, AI, I actually used AI in decoding errors in my quantum error correction experiment. And in the same way, AI can use quantum computers that you see in the data centers, like replacing the QPUs and the quantum chips, not replacing, but complementing these chips with quantum computer to explore large parameter space. Okay, the question is, will quantum replace classical computers? And the answer is absolutely not. This is not going to happen. And the analogy here is, you can think of classical computers as the lamp that we see at home. And you can think of quantum computer as a laser. The laser is more powerful than the lamp, definitely, right? But the laser doesn't replace the lamp. The lamp will stay because it's more efficient, it's more cheaper, and so on. And quantum computers will only be used in data centers because they need large amount of resources that you cannot have everywhere, and it's quite inefficient to actually have everywhere. So we will use quantum, but only for specific applications, called tailored applications, what people call co-design. If you have a problem, you're trying to optimize the solution to solve that problem and tailor that by quantum computers. So I find this analogy quite accurate. Okay, what a quantum computer looks like. In my work, I worked with superconducting qubits. Superconducting qubits use superconductors to encode the quantum state, but superconductors are quite dissipative at room temperature, so they have to be cooled down to the millikelvin, almost to the 0 Kelvin, or the absolute zero, what we call it, with a dilution refrigerator. This has a lot of wires that goes from room temperature all the way down to where the device could be. So this is here the actual device, and these have different thermal stages where you can achieve you can go down with temperature all the way to 10 millikelvin here. The device looks like this. It has a lot of CBWs and microwave components on the device. The actual qubits, or the unit for bits, as an analogy in quantum, it's called qubits. They are shown here in the bold colors, or the obvious colors here, and they are connected by some waveguides and to control and to be able to measure them. They are fabricated in the clean room. And then at room temperature, you have all these microelectronics in order to send all these signals down to the device and to be able to manipulate and measure qubits and to perform computation. And at the end, there are physicists and engineers who are sitting behind the computer and programming and setting up controlled experiment, and of course measuring, taking analysis or performing analysis and taking conclusions, and doing this iteratively in order to perform these computations better. Okay, what is it that I do? I wire up the device on the bottom of the dilution refrigerator. I I operate the cryo setup, so I run the dilution refrigerator in order to achieve this 10 millikelvin to isolate this device from the outside world, and that's what takes most of the energy. What Dr. Alexander was saying, it's a dilution refrigerator that is kind of a power hanger that actually consumes a lot of energy, because you want to isolate your device from the outside world, from the noise, from the mechanical and thermal noise around. So that's why you cool it down with this dilution refrigerator. So maybe there is a lot of research on that, like how to get efficient dilution refrigerator and to minimize their energy consumption. After that, I built the microwave racks, the control racks that actually output the signal that you want to send down all the way to the device. So here you see some signals with certain shapes. So I want to see that the signals I want is like as intended, they look as intended, and they are sent down to the device to manipulate and measure qubits. And then at the end, you sit behind the computer, you try to program controlled experiment, you measure and analyze data, and then you take it like you do trials, you take the conclusion, you move to the next experiments, and so on. And everything goes well. If everything goes well, then you write papers, and which doesn't happen that often, but it comes after a lot of hard work because data and data from experiment can be very tricky. Okay, my PhD work is actually about how to realize this good copy of states. If you recall what I called the copies of states, since we know that an error will happen no matter what, so we create so many copies of the state that we want to protect. And this protected state is called the logical state. So we want to create this logical state with low enough error rate that is better than the physical error rates of these copies, right, of the physical copies. And we encode that in a small number of noisy physical qubits. So I started my PhD with a 4-qubit device. Here you see the actual qubits, how do they look? And you see the waveguides that actually couples them and control them and so on. And I had to scale that up to a 7-qubit processor and a 17-qubit processor. So my last PhD project was about implementing this or realizing this logical state in a 17-qubit processor. So each of them are noisy, but I will create an effective state that is better than any of the physical state. So that's the experiment that I want to perform with this processor. So I don't want to go deeply on technical level of what is exactly that I did, but I want to provide an overview for people to be able to follow and understand what I roughly did. So you can think of any experiment as, or a quantum experiment as a pyramid with increasing complexity. At the bottom of this pyramid, there are the basic building blocks, such as single qubit gates, 2-qubit gates, and measurement. And you need to calibrate these building blocks to good high fidelity, and also with low error rate. You need to ensure that these building blocks have low enough errors that you can use them to perform algorithms, right? So this is the first layer. You make sure you have these building blocks with high fidelity and low error rates. The second layer is the detection layer, is this framework to perform computation and to be able to detect errors with what we call parity checks. So they are more complex than these isolated building blocks. They use this in a certain order. And the job here is to, again, to calibrate, to benchmark, to be able to daily monitor the performance as the device performance drifts a lot. And then at the end, to be able to implement a certain algorithm, right? You see that the circuit depth is increasing as I go up in layers, right? So it gets more complicated, calibration becomes harder, and so on. But I want to tell you that in our last project, as you know, that experiment is quite tricky to handle. And you see here on the y-axis, I show the logical error rate. So it's the error rate of this protected state that we want to protect, right? And here you see how many times we try to improve this on the same device. So this is not a different device. And we keep trying, doing an experiment, understanding what limits the error rate, doing it again and doing it again and doing it again. We were able to reduce that error rate from 13% to 4.7%, so almost 3 times lower than what we started with. So this is how experiments go. This is how like quantum labs work at the moment. They take a lot of time in order to understand what limits the device performance and to be able to improve that error rate. Okay, any questions so far?
So, yeah, that's really great, Dr. Hany. Very impressive work indeed, and it shows complexity in simulating the hardware and also to get things done from the qubit. So that's very nice. So okay, let's have a question from Karim.
Hi, thanks a lot for your talk and congratulations on your work. It's really amazing. I have a question regarding the connectivity of the hardware. Is it like a fully connected superconducting platform, or
You mean the
you need
physical
it?
layer?
Yeah.
Yeah, it's called the surface code. Surface code means that the qubits are connected in 2D. It means it is connected on the surface, and next the nearest neighbor qubits are connected. So this qubit is connected to this one and this one, that they are the neighboring. Maybe you can take a qubit in the center. Every qubit in the center is connected to 4 qubits. So this is the connectivity in the middle. Maybe at the edge it has less connectivity, but this is what's called the surface code. So connection is done, or qubits are connected in 2D, is only in 2D, right? So this is called the surface code. It's quite modest on the quantum hardware. It's easier to connect qubits on the surface than having a third dimension, which is quite complicated. So this is called the surface code, by the way.
Okay, great. And regarding like the crosstalk noise, or like the effect of, like how could you manage something like this?
Yeah,
if
that's
you
a
can
good question. Yeah, that's a good question. So another layer that I haven't talked about here is when you move between layers. As I said, I start with this basic building blocks. It's like you are trying to build a circuit. So you literally improve each of the individual building blocks. And as you move to this circuit, which is different from this circuit because these are isolated things, are isolated operations, right? When you move to this circuit, you see that like when you implement this, the performance here of each of the individual blocks, they are different from this performance here because of crosstalk, because qubits talk to each other, because, there are various crosstalk effects and various crosstalk types. I won't talk about all of them, but part of the challenge here is to be able to calibrate or recalibrate these building blocks in a way that they will run in the actual circuit. So kind of mitigate some of these crosstalk effects by saying, okay, these operations feel each other, depend on each other. So we are not going to only perform calibration when they are isolated, but we will perform calibration when they are all together, or when they are somehow all together. So there are a lot of technical details here. If you want to go technically, we can go to each types of these crosstalks and what that means
I
and
only
so
have
on.
one more question, and that's it.
Sure.
Like, for example, how much can you say about like the gate fidelity, or like the process fidelity itself? Like, let's say, for example, I want to, if I have like a very simple unitary, like a 1 qubit unitary, and I want to make sure that it's going to be applied like at least with 99% fidelity. Is that doable on the platform that you are using? That is one thing. And the other thing is, like, are the qubits, are they dynamic? Like, can I, for example, like measure one and then reset it to ground, and after that use it one more time during like a single iteration for like any algorithm that I want, or this is not possible? And that's it. Thanks.
Okay, thanks for the nice questions. First is the question about fidelities. Of course, we are trying to maximize fidelities the best we can get. The best error rate for these building blocks are a bit different. So, for example, for single qubit gates, we can achieve 3 nines, which means 10 to minus 3 error rate. Right, still not great, but it's good. For 2 qubit gates, I actually show here randomized benchmarking for one of the 2 qubit gates here, and they also show 3 nines, but this is the best performance, not the average performance. The average performance is about 2 nines, not 3 nines. So this is one of the limiting operations that we want to improve. And if you were to go for, especially for error correction, you really need every operation to have an error rate less than 1%, and actually far less than 1%. Ideally, you should have all operations that have 10 to -3. But I'm saying on average for these 2 components, at least they have 10 to -2. So it's a challenge to get them to 10 to -3. So we want to do calibration and improve our design, improve our coherence, the error budget that contributes to this number, to this error rate, to improve performance overall, to be able for the error correction to take, to be effective. Because if you create all these copies from noisy qubit, the physical performance is quite bad. Then the performance of this state, the global state, will be even worse than each of the individual physical states. So you need these fidelities to be very good, the physical fidelities of the operations to be good to start with. The second question was, I forgot the second question, sorry. What was
it's
the
basically
second question?
related to dynamic circuits. Like if I have a qubit
Yeah.
that I want to measure and then apply a reset operation to it so that it's a ground again, and then reuse it if I wanted to reuse it. Is
Yeah,
that possible?
Yes, it is definitely possible. It's reset operation requires feedback. So, for example, if you want to reset the ancilla qubit here, this is called the ancilla qubit that has a Hadamard gates and some 2 qubit gates, and then measure. After the measurement, if you want to reset that, there must be connected to some feedback to your control electronics in order to reset the qubit, right? In order to be able to perform conditional output or conditional gates based on the measurement outcome that you want to see, or in order to totally reset it, like remove the photons from the resonators, for example. So that's totally possible, but it is challenging at the hardware level. It's not that easy because you need to perform this feedback, and you need to have low enough latency to go full way, like from your control electronics all the way to the device. So it's not very easy, but it is possible, definitely. And a lot of people are exploring also dynamic circuits in the sense of dynamic algorithms. Like it's a very active area of research. But again, the hardware should be able to perform feedback in order to do reset, or you have some people even do specific quantum design in order to perform reset. So there are a lot of technical details here, but I would say it's possible. It is very possible to do dynamic circuits in this processor. Okay.
The other, and maybe a quick comment. The other way to leverage the low fidelity, in quotes, low fidelity, is to have very short circuits.
Yes.
Right. If your error rate is reasonably high, but you don't have to do many gates, you're still likely to get a good result. I mean, I think this was the big advantage of the early VQEs, right?
Yeah. Definitely. Yeah, definitely. It's the trade-off between circuit depths, is how many operations you run, like in space, like you repeat these operations for how long, and the fidelity. If you run operations lower than the fidelity, like for the fidelity that allows you to stay without having an error, then you are fine, right? You're probably good to go. So a lot of people believe that maybe we don't need to create so many copies of the state and run it for very deep circuits, because that creates a lot of problems. And maybe we can run shallower circuits and combine these circuits all together to reach a certain algorithm, like to get to a certain algorithm. So based on how you design your circuits, it's a trade-off between multiple parameters. These are the circuit depths, or the fidelity, or even the coherence limit of your qubits, right? Okay.
Yeah, thanks a lot, Hany, for this. Just the sake of time,
Yeah,
we just
definitely.
limited question here, but thanks very much for this informative, interesting talk, because it really shows the complexity of building the quantum platform and the simulations and how to keep the errors at a very low scale. So that's a challenge from the hardware side. So our next speaker is Alain Chancé. Just before moving forward, I would like just to apologize. We had a certain sequence of presentations that's based on a table that has been updated recently. However, the text as it was associated with the table was just not echoing the recent updates in the table, the shared table. So I would like now to introduce my next speaker, Alain Chancé. I'm just sharing. Okay, he's already shared the bio. Okay, that's great. So Alain is the president of MolKet SaaS, and MolKet, of course, a startup that we co-founded. You know him now for many times because of being associated. Thanks for him to give presentations on Quantum AI monthly series. And MolKet is a member of QEDC and QUIC, and MolKet is offering management consulting and AI services in quantum nuclear dynamics, cryptography, and neuromorphic computing with cloud-based hybrid HPC and quantum computing platforms. And I also is the founder and CEO of Quanta Alain Sassou and Alain Quant LLC, and both businesses management consulting startups. He's also Qiskit advocate and IEEE senior member, a society affiliate of the American Chemical Society, and a member of the American Physical Society as well. Alain also serves as an advisory board of Committee in North America Technical Institute in Virginia, which offers a professional certificate in quantum computing, and he also was a panelist in the Quantum and AI Use Cases panel organized by QEDC, and he participated in IBM Quantum Developer Conference in the States, in New York in last November. He also was a keynote speaker and co-speaker in the World Artificial Intelligence in Cannes Forum in 2024, where he presented combining the power of AI and quantum. He's also the co-author of this nice book with Keeper Sharkey, Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code that was published in 2022. And also Alain has several years, over 30 years of experience in major enterprise transformation projects. And he also holds a diploma in Engineer Civil Demine from École des Mines de Saint-Étienne in France. Yeah, Alain, please go ahead.
Sorry, I was on mute. So let's start again. Thank you, Taha, for your nice introduction. Hopefully, now you see the next slide. Can you confirm you see the next slide? Can you confirm, please?
Yeah, I see abstract. Yes.
Thank you. So, so today I will present an outlook of quantum AI agents and practical use cases, underscore 10 times practical. Okay, I'm not an academic, by the way. I'm by training. I've been throughout my life transforming dream into reality. So I'm like an executive engineer focused on practical use of cutting edge technology. Okay. So the agenda. These are all the slides I prepared for you today. Some of these slides I've already presented in past presentations, but this is an excellent introduction to what's available today in terms of classical AI agents, a vision of quantum agents in a network, and then gradually we will move from pure classical AI agents to quantum AI agents, and we'll see great applications there. Okay. So first of all, the definition. Let's define agents. Have existed for a number of years, but AI agents is more recent. They are systems or programs which are designed to perceive their environment, make decisions, and act autonomously. This is the very definition of an agent, autonomously or semi-autonomously to achieve specific goals. And AI agents are central to many applications of AI, ranging from chatbots to robotics and also complex decision-making systems. They are increasingly being applied in chemistry, leveraging their ability to process vast data sets, understand maybe that is still a hotly debated topic, whether they actually understand or not, understand complex concepts and generate insights for various applications. On the left-hand side, a nice drawing from Bray Kishore Pandey illustrates the AI agents. They are when used in network, they deliver much more. And actually, AI agents now there are frameworks that exist independently of the LLMs. Okay. What is quantum robotics? Basically, robots that leverage the probabilistic nature of quantum mechanics to expand the scope and capability of robotics. So they are called also Q-bots. Now, if we push to the extreme, and we can think about quantum agents in a network where there is no classical processing. It's all quantum sensing. On the left-hand side, you see a nitrogen vacancy NV center in a diamond quantum sensor that feeds into computer A, quantum computer A, that interacts with quantum computer B. And we can think about pure quantum communication there, and the processing can also be purely quantum, and that is interesting. And so there is a nice this diagram comes from a nice article. The title is funny: "Do qubits dream of entangled sheep? Quantum measurement without classical output." This is the challenge with mainstream quantum physics. You need a so-called observer. You need a measurement made by an observer, and it is assumed, though it's not crystal clear, that the observer is a human. And in that case, there is no human. So they had to put forward a new concept to be able to talk about quantum measurement without classical output. But this is very exciting because we can envision in a foreseeable future an experiment that would help theorists, quantum physicists, better understand, better model the still fuzzy notion of measurement. Okay. Now, purely classical, but yet in full production, the IBM Robo RxN for chemistry. It's a good example of a cloud-based, AI-driven, autonomous, therefore an agent, chemical synthesis robot. Has been built on a digital chemistry platform, which is called IBM RxN for chemistry. Has been online since 2018, so before the hype around large language models and agents. But it has been used by more than 29,000 users who have performed over 5 million reaction predictions. So it's quite simple. The human, the chemist, simply has to copy-paste paragraphs of presumably their his or her notebook, and feed that into a text box, and Robo RxN then plans a standardized list of actions that is handed over to a automation hardware. So it's chemistry lab automation, if you want. What's interesting is that users can train RxN with their own data sets using proprietary knowledge for customizing their prediction models. So this is pure classical, but yet I would say a well used AI agent in chemistry for lab automation. Now, on top of that, there is ChemCro, which is an LLM chemistry agent, which can be used on top of that to implement a so-called chain of thought reasoning loop. So the chain of thought reasoning loop has been used quite successfully in the world of large language models, and it is summarized on the right hand side. So number one, reason plan from input from a human, and number two is to select a tool. So this is where there can be a number of different tools, Google, as well as Google search or some other large language models, or it can be agent-to-agent communication and collaboration. But also it could be the tool we talked about in the previous slide. It could be IBM Robo RXN. So it and also it provides added value with the safety tools. So this is a very good example of a value of an LLM which delivers value in a well-defined scope for the accurate solution of reasoning intensive chemical tasks. And you can try it out on Hugging Face. I'll give the link on the left-hand side. So we have just covered two good examples of classical AI agents for chemistry. Now, what's going to happen? There are key thought leaders. MIT, one of them, John Lee, for example, says, looking ahead, the next wave in AI development is physical AI, powered by AI models that can understand and engage with our world and generate their actions based on advanced sensory input. So a number of experts in the field of AI claim that we will never reach so-called human-level intelligence with only LLMs, large language models, which are very useful. But if we want to really achieve major breakthrough, we need something different. And the idea, and it is shared by Jack Hidary, the CEO of Sandbox IQ, is that we need AI that models the physical world, not just language. And they call large, instead of large language models, they talk about large quantitative models, LQMs. And these LQMs are much smaller in size as compared to, they don't need to be so large as compared to large language models. And they can be focused on fields like physics, chemistry, and machine learning to solve real world challenges. Okay. And what's interesting is that there is convergence between this view of what's going to happen in the coming years with experts in molecular simulations. Back in 2023, there is a paper from Jun Wang et al., which claimed that physics laws can play the role of regularizer and help AI models to learn faster and generalize better, and it would avoid hallucinations, which is the annoying bug or concern with large language models, when they deliver output, which seems to make sense, but actually is false, is completely invented, and sometimes completely against the reality. Now, but with AI models, which are based on physical models, and which get their input from advanced sensors by construction, that's not going to happen. Okay, but again, there we are still in the classical AI world. So let's move on to the quantum AI world. So it's interesting to note that a number of key players in the field of quantum computing now claim that they have already achieved some success with so-called quantum-centric supercomputers. That is to say, integrating high-performance computing, HPC, or supercomputing, with quantum. And a good example is the collaboration between IBM and Pascal. They aim to provide a hardware agnostic framework for the classical quantum integration, integration of classical and quantum for quantum-centric supercomputing. And so I give the link to the announcement at the bottom of this slide. They're not the only one. Quantinuum, more recently, February of this year, unveiled what they claim is the world's first generative quantum AI. So you've got everything there, generative AI and quantum. And you can see on the right-hand side in this slide, it's a loop. So you can think about starting with, say, AI to frame to scope a problem, which is then handed over to a supercomputer. And then the supercomputer, for instance, identify a Hamiltonian, and then the quantum processing unit or the quantum computer merely does sampling from a quantum from quantum circuits, and then that goes back to AI, which can check the output, and then you can have a virtuous loop. Okay, and they claim that this quantum AI framework can tackle complex problems which are impossible for classical computing. Okay. There is another example, but there are actually so many. I just illustrate with just a few. So the POSE Supercomputing Research Center, which is based in Australia, and Quantum Brilliance, which is they claim a global leader in mass deployable room temperature diamond quantum technology. They're also based in Australia. Now they have put forward a seamless integration of GPUs from NVIDIA, some of the biggest NVIDIA GH200 Grace Hopper super chips, CPU, actually high performance computing, and quantum processing units from Quantum Brilliance. And they say their workflow is operational. And key application of this technology include radio astronomy, data processing, AI workflows, and bioinformatics. And I guess also it would work for quantum chemistry or quantum molecular dynamics. Yet another example, this time from Microsoft Azure Quantum. They have, well, it is on their website, but this is also explained in the paper, which I give a reference at the bottom. And there is an extract from this paper, which is the workflow. And I've summarized on the right-hand side the way it works. So it's for end-to-end quantum simulations of a chemical system. So the classical high-performance computer finds candidate molecules and outputs an active space Hamiltonian with a reduced dimension. So this is the key, is to focus what's going to be handed over to the quantum computer. And active space Hamiltonian, which is much simpler to then simulate using quantum circuits. The quantum circuit merely samples the quantum state. That's the only thing it does, but it does it well. And finally, last but not least, an AI model learns from the quantum measurement data to predict the ground state energy or some other interesting quantity. So in other words, the AI model there, it's basically a surrogate model from a few measurement data points, which have been hard to gain to predict more. So you see a very good example of synergy between high-performance computing, quantum computing, and AI, classical AI in that case. Okay. Now, I promised practical use cases. This is the first one. IBM, Cleveland Clinic, and RIKEN in Japan. They are exploring chemistry research with quantum-centric supercomputers. So IBM, in partnership with RIKEN, they have explored a method they call sample-based quantum diagonalization, SQD, for simulating chemistry with quantum-centric supercomputers. Actually, yesterday, there was a great presentation by IBM about the SQD method, which can be used not only for quantum chemistry, but for some other use cases. So what is SQD? It's a classical post-processing technique which acts on samples obtained from a quantum circuit after execution on a quantum processing unit. So basically, it does some heavy lifting. Actually, it does the diagonalization of a Hamiltonian, which is represented as a matrix, and then it solves the Schrödinger equation and finds the eigenvalues and the eigenvectors, and the eigenvectors give the position of the electrons, and the eigenvalues give the energy level. What's interesting is that, and it's in plain sight, IBM and again, they explain that it would take 3 million years to model an iron-sulfur cluster using the so-called variational quantum eigensolver, VQE method. And by comparison with the IBM's Heron processor and Riken's Fugaku supercomputer, which is the most powerful in the world, I believe, running SQD, the same modeling can be achieved in just 2 hours. Okay, there we are. And I give the reference at the bottom. Now, something essential to understand, it's not just a matter of adding a QPU, a quantum processing unit, to a supercomputer, which basically runs a bunch of GPUs. Now, there is also, it's not just a technical integration, there is hard work there. A multidisciplinary collaboration was essential to achieving this framework. This is what the team leader, Dr. Rob Arnold, said. What's interesting is that they claim that this quantum classical hybrid framework, the initial results outperform both a classical physics-based method and AlphaFold 2. AlphaFold 2, very successful AI application that that has been used successfully to predict the folding of proteins. So there we have a practical example of an advantage, but it's not achieved with just a quantum computer. It's achieved by a very well-designed synergy of HPC, quantum, and AI. And Dr. Robinhold states that, and I quote, "Our team's expertise ranges from computational biology and chemistry, structural biology, software and automation engineering, to experimental atomic and nuclear physics, mathematics, and of course, quantum computing and algorithm design. It took the knowledge from each of these areas to create a computational framework that can mimic one of the most important processes for human life." I think this is very important. Such an advantage cannot be achieved simply by adding a QPU to a high-performance computer and running a classical algorithm. No. This is something completely new. And I think it paves the way to many more exciting applications. But this is really hard work. There is another claim, this time by University of Toronto and in silico medicine. They have combined quantum computing, generative AI, and classical computing methods. They say that they have been successful creating molecules targeting a cancer-driving protein called KRAS, which had previously been considered undruggable. So Alan Aspuru-Guzik, who is a world-class expert in quantum chemistry, among other things, claims that this first-of-its-kind study shows that AI, with the help of quantum computers, can successfully find molecules that interact with biological targets. And I give the reference there. Okay. Now, this is MolKet. MolKet SAS was co-founded by me and by Taha Selim at the end of last year, of 2024. What we offer is management consulting and AI services for quantum molecular dynamics, cryptography. For instance, on Sunday, of last week, I made a presentation for ICCC-AS remotely at the foreign conference based in Wuhan, China. And the topic of my presentation was quantum permutation pad, which is a symmetric cryptographic protocol, quantum permutation pad with Qiskit Air. Okay, and we also aim to provide services on neuromorphic computing. We believe neuromorphic computing has very good applications, very promising, and we leverage, I would say, humbly, laptops, powerful laptops, cloud-based hybrid high-performance computing, HPC, and quantum computing platforms. For example, we have open plan with IBM Quantum, which enable us to, me in particular, to run for free up to 10 minutes QPU time on some of the best available quantum processing devices from IBM, which is great. We also provide consulting services for training AI on data sets from fields such as chemistry, biology, material science, and cosmology. Now, we have, but we haven't got the time to present that today. But for those interested, we have a website, and on this website there is a tab which leads you to a GitHub repository where you can see some of our work. We write stuff in many different languages, Fortran, Python, but we like Julia a lot because it is as nice to use as Python, but the big difference is that performance is comparable to what we can achieve with Fortran or C++. I would just mention that I've noticed a huge performance improvement with Qiskit, moving from Qiskit 1.3, Qiskit software development kit, Qiskit SDK, moving from 1.3 to 2.0. For example, for my QPP work, one experiment, the elapsed time was reduced from 15 minutes, was for the QPP 8 qubits, down to a few seconds. Absolutely amazing. The same for the Jupyter notebooks, which illustrate my book, Quantum Chemistry and Computing for the Curious. And one of the reasons why this has been achieved by IBM Quantum is that they have rewritten the kernel of Qiskit with Rust. So moving from Python to Rust gave this huge improvement. And I think it is worth thinking about whether it is worth developing stuff in Python in the first place, then to rewrite stuff in Rust or some other language. Why not start with a powerful language such as Julia in the first place? So that's it for me. I will share my deck of slides. In the deck of slides, you will see an extensive bibliography. Okay. And also a glossary of terms for those of you who are maybe more familiar with quantum computing, but not so much with AI. So that's it for me. I'm open for questions if there is time and if there is any question. Hello?
Just my camera takes really time to work. Thank you very much, Alain, for this nice talk and very clear explanations about this quantum AI use case. So please feel free if you have questions. So now we used a different style. We're supposed to have the question and answers at the end, but now they are following the presentations directly for a few minutes. So if you have a question, please raise your hand. Okay, so I would like to ask Alain about this. So now, how can you, or how you can, for example, extrapolate to the quantum advantage which potentially can happen from combining the AI agent structure with quantum computing. How you can see, do you see this feasible within this structure? And if so, how you imagine it?
Well, I think I've shown evidence that this has been implemented. So, and I think it's the good news that we can foresee a gradual incremental progress from, I would say, more supercomputing, more HPC, and more AI, and the quantum computer role humble, but nevertheless essential, just sampling, okay? And then gradually, when quantum processing units become more powerful, then hopefully, but I'm positive, the added value, this is the missing term, the added value, this is what matters, okay? The added value of the quantum processing unit will increase in the mix, okay? And I think the good news is that we don't need to wait until so-called universal fault-tolerant quantum computing is available. Maybe it will never happen. We don't know. Maybe we'll only achieve partially error-controlled quantum processing units, which still need some. It's okay, but the good news is that right now there is evidence, and again the key point is that it's not a simple matter of adding a QPU to a mix. It's back to the drawing board. People need to redesign algorithms from scratch, because the early ideas of using, for example, QAOA or VQE, I mean, there are barren plateaus and the like. It's very good to get trained on quantum computing, but for practical purposes, those who will succeed need to put together multidisciplinary teams and invent new hybrid algorithms from the start, and that is, I think, very, very exciting.
Yeah, thanks, Alain. So Alex Khan, so welcome, Alex. He has a question, so nice to see you.
Yeah, definitely, Alain. Nice to see you. It's been a while.
Yes.
So my question is, are you seeing any advancement on the neutral atom system side? Because, you know, those were going to promise us ability to simulate molecules. And also, you just mentioned different algorithms, so Lie algebra or other techniques, I think. Have you seen other techniques that are improving the whole process?
So first of all, yeah, I'm more familiar with the IBM platform and therefore superconducting loops. But what's interesting, for example, is the partnership between IBM and Pascal show that it's still an open race. It seems that for now, superconducting loops are in the lead. But it's really a question of scalability. Okay, all the players. So the neutral atoms, the Rydberg states. I guess Pascal is one of the key players there. They are very confident. By the way, I think they also have provide services with GPUs. They have Pascal have a partnership with NVIDIA, and so I think it is the same challenge to invent new algorithms fit for purpose. So far, I think the whole industry of quantum computing has been a solution looking for a problem. Okay, but now that there is more maturity, first of all, there is impressive progress around error correction on all sides. IBM, I guess Pascal and others, also for the ions continuum have shown, Google have shown amazing improvements in quantum error correction. Okay, so then pertaining to the algorithms, there is a bunch of new algorithms I've heard about, but I've not yet experimented with. There is the DQE algorithm, basically, that don't require gradient descent, because the gradient descent, which is handed over to a classical computer, it's not fair. The classical computer has got to do the heavy lifting, and it is not. I mean, Barron plateau and the like. So there are new algorithms which have been put forward where there is no such thing as gradient descent. There are also new algorithms which without back propagation, and I think these really need to be tried out.
Yeah, definitely. I think the algebra, from what I was reading in one of the papers, seems to avoid the gradient descent. At least that was my impression.
Yes. So I think this, again, based on the experience of the last couple of years, these algorithms, which do not require gradient descent handed over to classical computer, are very promising. If there was a way to do a gradient descent quantumly and leverage, for example, tunneling, I mean, that would be fantastic. But I've not heard of anything like that. I mean, that would make sense, right? I would say, okay, then try to find the true minimum in a landscape where there are many other minimums using quantum computer. But this is not the way. Until now, it has been put forward, and I think this is also an area of research for. So basically, to in a nutshell, we have new exciting hardware. Now is the time to come up with new algorithms. Yep. to innovate and tackle real use cases.
So, yeah, thanks very much, Alain, for this nice and clear presentation, and thanks very much for highlighting the use cases. And thanks, Alex, for your question. Now we're going to move to the next speaker, Ian Blommaart. Just allow for me 1 second to share my screen. And after Ian, we are going to have a presentation from William Slater.
Hello.
I'm just sharing that to introduce you. Yeah. Okay. Yeah. So Jan Blommaart is going to talk about updates about the IBM new quantum platform. So Jan Blommaart is a managing partner at BioDAC, Data Analysis Center for Life Sciences, and he provided data analysis services to various industries like food, agriculture, government, and science labs. Has several current projects on machine learning applications, including quantum machine learning and spectrum analysis, classical machine learning for weather forecasting and Earth observations, and the machine learning in enterprise asset management. He had previous projects involved HPC deployment for radio astronomy, yield forecasting for potato crops, large-scale storage system designed for HPC, and advanced semiconductor technology for low-noise radio receivers. He worked in large IT and consulting firms since 1983, and he's has a background in physics from TU Delft in the Netherlands. Yep. Please go ahead, Jan.
All right. Here I am again. 1 second. Okay.
The slide is not visible yet.
Yeah, well, 1 second. I need to start it here. Why is it? I don't understand what's happening. Should be good. Okay. Okay, can you hear me? Can you see the screen?
Yes.
All right, thank you. So, what I will explain in a short introduction is how you can today use real quantum computers. Yeah. And I will show some examples of how the direction is going. Yeah. And in the end, I will propose how you can start. Yeah. Like we said earlier in the several talks today and earlier, we do think there is real business coming. Yeah. And you have several industries for which it is interesting. A large one is obviously in healthcare and life sciences, and also in fraud detection and in catalysis. So many things around material and chemistry. And you can divide them again, yeah, in problems that are classically intractable, but that could be done in a quantum computer. So, like earlier said, we will always have a combination of quantum and classical computing. And we need to find the right problem for the right platform, yeah? And the right problem for the combination of these two. So it's chemical and material simulation, as has been said earlier. Yeah. Possibly machine learning, yeah, and then optimization and linear algebra. When you look at the IBM stack, they have the platform and they have the software, and on top of that, applications. I will talk a little about the platform and the Qiskit software. But first, we need to talk about the concept of performance. Yeah, there are several aspects to it. One is obviously the quality. So when you have a lower error rate, the quality is going up. And the other is scaling. So you have a larger processor so that you can handle a larger problem. And you can fit all different architectures, different brands, different vendors with these two axes in terms of quality and scale. And there is a whole range of benchmarks that you can apply, and then you get a picture like this. And what you see is that in the right upper corner, where you have higher scale of problems, higher scale of machines, and higher quality. Yeah, that's where we want to be. And obviously, we need to go much further. Yeah. But there's another aspect to it. That is speed. Yeah? How fast can you execute? How long does it take to solve a given problem? And cost, the cost of running. Yeah. And we are pretty sure that there will be big differences. Yeah. As you may know, there are quite a few vendors that have superconducting qubits as the platform, the physical platform for their qubits. And one competing platform is the ion trapped ions. But there will be enormous differences in execution speed. Yeah? And secondly, because of the nature and the physical properties and the physical design of the quantum devices, there will be enormous differences in running cost. Yeah, and this is very important, not for a small experiment, but once you really think about, real applications, cost is very important. We discussed it earlier in this session about the energy cost, and it's all related. Yeah. And here you see an overview of the current quantum computers that are available today in the global cloud. Yeah. And once in a while, these machines get replaced by newer models and more stronger, more performant ones. Yeah. So gradually you will grow. The smallest is now 127 qubits, and they will grow gradually to the larger ones that have 156 qubits. And the next generation will be better in quality, yeah, and probably much faster. What you see here, and it's all measured, it's all published, these numbers, yeah. So you see the number of qubits, you see the error rates, you see an execution speed number, which is the clocks, there's the number of circuits per second, yeah. And there you see quite a difference. And this is important for having a real-time advantage. Yeah. Okay. And then in the coming years, we can foresee that in the cloud, in the IBM cloud, we'll find better machines. And around 2028 and 29, we will see a tremendous improvement. We think, and that's what you will see, there will be very close integration.
Jan, there is a problem, and so we see only the introductory slide.
Hey.
And yeah, we don't see the rest of the slides that you are presenting.
Oh, 1 second.
Yeah.
I will stop sharing, and then let's see what happens.
Right.
Yeah, maybe I what I will try, I will not use my full screen, but just let's see if that happens, if that helps. Yeah. Can you now see this one, Taha?
Yeah. Yes.
So let me go back to the beginning. So I talked about the market that is expected. I talked about the different categories of problems, and that you need to, really think about what is the problem, what kind of problem am I trying to solve, and what algorithm fits to it, and what platform is the best for executing solving the problem. Yeah. Then I talked about the full stack. Yeah. So you have the quantum hardware in a data center, and you have the development kit. And here I talked about comparing different architectures and doing benchmarks in order to understand what the quality is and what the size of the problems is that you can address. And here I discussed the important aspect of execution speed and the aspect of running cost. Yeah. And it's we think there are enormous differences between different architectures when it comes to the cost of running problems and the speed with which you can solve a particular algorithm. Now here I show the number of quantum computers that are online available today. Yeah. Officially, you cannot do production work officially, but in practice, I can tell you that the availability of these machines is very good indeed. Yeah. So that's an enormous advantage of this approach. Here I showed the roadmap. Then I showed this one, how the integration will be between CPUs, GPUs, and quantum computers. So this is about the hardware. Then the software. What is extremely important is that it's all open source. Yeah, that you can port, you can discuss your design, you can publish your design, and you can port it from any platform to another, so that you can really take advantage of the new technology as it becomes available. And what is clear is that a very high number of users globally is developing in this Qiskit toolkit. And very recently, the new software development Qiskit version 2 was available. And there is the notion of what they call the Qiskit functions catalog, which helps to get very abstract and well-defined functions, so that you have less need to know a lot of detail. Yeah. This is what we can expect for the coming years. Yeah. So we are now in 2025. We are about to see the quantum advantage for useful business problems next year. Then in 27 we'll see a path to error correction. In 2028, the first error-corrected quantum computer will be online, will be tested, and will be shown, announced. Now, what is very important is that people start doing coding and really learn. What I can highly recommend is the following. In a couple of weeks, in July, there will be the new global summer school for 2025. And I would highly recommend that students in particular, but anybody can register for this summer school and learn from the very beginning. You learn how to code, you get access to excellent machines, and you get very good mentoring. And this is a really nice way to start your career in quantum computing. This is it for now, Taha.
Yeah.
I'll stop sharing.
Yeah, thanks very much, Jan, for the nice presentation and the current updates about quantum computing platforms, especially in IBM ecosystem and also provided by IBM facilities. Yeah, thanks again. So please feel free if you have any question to raise your hand. So I can have a question myself.
Yeah.
Now about the plan of IBM. So Salim has a question. Let's just read the question of Salim first. Is the quantum cloud actually being used in industry today? Which industries? Out the data centers? Out the data. I would think he means out performing the data centers are using this technology, and which companies are leading the way?
It's I mean, you have several industries that are available, that are using the platform. One area is the financial industry, banking and insurance. Another area is oil and gas and chemistry. Another area is pharmaceutical companies. Actually, you have laboratories and universities. So in total there are about 250 companies and institutions that are part of what they call the IBM quantum network. And there are many individual users, a few 100,000 who are using this system.
So thanks, Jan. So I would like then to, for just the sake of time, I would like to move to our next speaker. So he wasn't planned, but he like nicely volunteered to give a nice presentation. So our next speaker is William Slater, and he's gonna present about Quantum Foundry. So let me present the speaker first. So William Slater is a president and the CEO of Slater Technologies, Inc. Is based in Chicago, and he's an experienced, certified, seasoned, and published IT professional with more than 4 decades of experience. He has been an adjunct professor for over 15 years and holds 3 master's degrees, including a master in cybersecurity from Bellevue University, if I pronounce the name of the city properly, and an MBA from the University of Phoenix, and 88 professional certifications, including CISSP, CISA, and PMP. His professional experience also covers includes the U.S. Air Force, Texas Eastern Transmission Corporation, Northrop Digital Equipment Corporation, BP, and the Department of Veteran Affairs, Microsoft, IBM, and McDonald's. He's a member of ICS Squared, PMI, ISACA, and the Internet Society since 1998, and founding member of QSecDev. And also, since 2001, his primary focus has been project management and programming management in cybersecurity, networking, databases, application development, and surface management, data centers, and the cloud computing. He has also worked in blockchain, artificial intelligence, and quantum computing, and generative AI and ChatGPT. So, yeah, he's a very well-recognized expert. And please let me, present Dr. William. Yeah, please go ahead, William.
Can you hear me?
Yes.
Good. I'm unfamiliar with sharing in this this video conferencing. Can you kind of guide me through what I need to do to get my
So next to the raising hand sign, there is an arrow points upward.
Oh yeah, it says present now.
Yes.
Okay, I can see that.
And then you will find three things: one from Chrome, one from Windows, and one to share the full screen.
Okay. I'll share full screen. And how do I get over to my presentation from full screen?
Then you just need to be in the screen where the presentation is sitting.
Okay. Oh, okay. I just got it. Can you guys see that?
Yes.
Beautiful. Okay. Thank you. Okay. I'm going to try to get through this real fast. A little disclaimer here. This is dated June 3rd. And I realized y'all had a couple of people that had to unexpectedly drop out tonight. So I guinea pigs and see this for the first time. A lot of work went into this, by the way. So the guy to my right, the gentleman, Joe Reddix, is my business partner. And we have submitted what's in this presentation to DARPA. DARPA's the people that do a lot of advanced research projects. They're also the people that invented the ARPANET and later on the internet. So they are kind of a big deal in the world of technology. I'm going to try to scroll down here. This is a little spongy, but I'm going to get through it. Okay. So the name of my presentation, I put this together. Joe was the reviewer. He also picked out the topic. It's called Building a Quantum Foundry. So I'm going to explain what that is in this presentation. When I was a senior in college, I had a manufacturing minor, and we went around to a lot of different companies, and I actually got to go to a foundry. So if you go to a foundry, it kind of looks like that. And they have sand castings, and they pour molten metal, and they spec out stuff, and they pour this metal in there, and they let, and it turns into stuff. So that's the good news. Now that we're into the day and age of quantum, there are these things called quantum foundries. that are coming into existence. And I'm going to give some examples of that. That was my agenda. Okay, so the introduction, basically, now we're living in an age where quantum computing and hardware, all this is rapidly growing. And so I'm going to talk a bit about a Quantum Foundry, and the emphasis of this is going to be on quantum sensors. And I'm going to get through this really fast because I know that you guys are tired and we're all running out of time. I've got 4 quick announcements in here. If people want to write this down, when I'm in Norway right now, actually headed back to Amsterdam on board a cruise ship. But if you write this URL down, billslater.com/quantum /quantum foundry, or billslater.com/quantum foundry, you will see this presentation. I'll upload it as soon as I get back to the States, which is going to be on June 2nd. So you will, everybody watching this presentation will get a chance to have their own copy. DARPA, as I mentioned before, our proposal's gone in. It's going to be a multi-million-dollar contract because they're attracting this type of stuff. We are featuring a quantum hackathon. Ours is going to be a little bit different. It's not going to be a 3-day affair like the one for the people in Alexandria, Egypt. We're going to drag it out to about 30, maybe even 40 days, because one of the elements in the hackathon is going to be teaching and learning and mentoring. So it'll be a very different type of hackathon, but we are going to sponsor one. And my birthday is October 3rd this year, so we'll probably start it on my birthday. Special bonus, 2 slides in this deck have a star with a little red $sign in it. These are slides designed to save you a bunch of money. Okay, so got a few definitions of quantum foundries. These are from people that are doing this stuff right now. And I'm not going to read this to you, just to know that people are telling people what the quantum foundry at their company or their university is doing. So y'all can read this for yourself. They've got one in Copenhagen. They've got one at UC Santa Barbara. And they've got another one, let's see, this is Quantum Processing Unit Foundry. A quantum processing unit would be something like Google's Willow processor, or maybe that's Microsoft. Anyway, we won't be doing full-blown processors, except Joe's got a little expertise in that, so we may change our mind. What are the benefits and advantages? Well, there's scientific and technological, there are strategic and economic advantages, talent development and workforce enablement, broader societal and scientific impact, infrastructure and ecosystem building, and also the advancement of best practices for security and quantum computing. So we'll just go and look at these at a top level here. On the scientific and technical advantages, accelerated innovation, standardization, repeatability, cross-disciplinary collaboration, and scalable fabrication. Under strategic and economic advantages, national and technological sovereignty, market leadership, and intellectual property creation and commercialization. Under talent development and workforce enablement, hands-on training and upskilling, and pipeline for the next generation of experts. Broader societal and scientific impact, enablement of breakthrough applications, and also a collaboration hub. Infrastructure and ecosystem building, reusable design and process, intellectual property, and supply chain development, and advancement of best practices and security for quantum computing. This is a identification of possible security issues, communicating those to stakeholders who are funding your Quantum Foundry, and also management of the security issues and hopefully putting those to bed. So quantum sensors, I'm going to have a picture of this in a second, but quantum sensors are different than standard quantum computing. They both rely on quantum physics in terms of quantum theory, but they quantum sensors, you can utilize quantum principles with quantum sensors without having a full-blown quantum computer. So that's where this gets kind of differentiated. Why quantum sensors? Well, classical sensors cannot measure phenomenon to the same degree of accuracy that quantum sensors can. And there's a really good explanation explained in this quote here. It says, devices based on quantum physics have allowed the precise estimation of the gravitational field, the detailed imaging of the brain, the detection of gravitational wave sources more than 400 million light years away. There's just so many things that you can do with quantum sensors that you can't do with classical sensors. So this makes them all the more valuable. Now this slide 16 is very important. If y'all can see this with the turquoise blue circle in the center, over up on the right hand side, it says we are here. So in the world of quantum sensors, it comes under a topic called quantum metrology, which is using quantum principles to measure physical phenomenon, some physical phenomenon in the universe. So when you get a copy of this deck and you're sitting there pondering this, just remember that this is differentiated between quantum metrology and actual quantum computation with a quantum computer. So how do quantum sensors work? Quite simply, it's a 4-step process: preparation of the quantum system, exposure to a physical quantity, measurement of the quantum state, and then data interpretations. What gets made in a quantum sensor foundry? Well, this is a short list of quantum sensors in use today. So quantum magnetometers, atomic clocks, gravitometers, accelerometers, thermometers, and LDAR, which is light detection and ranging. And here's another list that's not exactly the same, but similar. And then here's kind of a visual list. And the top in the picture in this slide, it shows how things are getting measured now versus how they would get measured if you were applying quantum sensor principles. So it's just a little visualization there. And the next slide here is an example of something called a gravimeter, and it kind of details the components of this. Some of this stuff, particularly this one, has a lot of complex parts, so it takes a lot of engineering to put this together. This is a nice slide that came out of a MITRE paper. A young lady by the name of Bacchus put this together. I think it had something to do with her PhD, but this is comparing traditional sensors to quantum sensors, and this just kind of runs the spectrum here: clocks, inertials, sensors, gravimeters, magnetometers, field sensors, and photonic. This slide has, by the same author, has to do with maturity of quantum sensors, and it kind of shows you in the spectrum. What's really nice about this slide is the color coding here with a little legend up on the upper right hand side. It shows you atomic clocks, inertial sensors, etc. And it gives you the maturity scale from laboratory demonstrations all the way up to commercial off-the-shelf products. These are the 4 steps that are recommended to facilitate the development and utilization of quantum sensors. And I'm not going to read this in the interest of time, but this is well laid out. This presentation is the type of a reference thing that you can pick up and just go over and really familiarize yourself if you want to get into this type business. This has the future and development challenges involving quantum sensors, going from all the way to basic and applied research, going all the way up to consumer and end users. And it's got the key challenges up in the black box there, and then key challenges too, which is like connecting with end users and researchers and accelerating the R&D pipeline. As you might imagine, there's going to be some people that really have to educate their audience in terms of, they understand their mission, but they need to understand your challenges as people that are practitioners and designing this stuff. The next slide, timelines and metrics to track development progress. So you will be able to report your progress to your stakeholders. They always want to know where the money's going. So this is years 1 through 3 in your Quantum Foundry, and then timelines and metrics to track the development progress in years 3 through 8. And then, excuse me, I've got some examples. This anybody that's going to get into this area needs to study these timelines, because if you go back and look at this timeline goes from 2001 all the way up to it took it from 2011 to the point where it was in production. So that took a good 10 or 11 years before that got into production. This is on atomic clocks, first generation. So it doesn't happen overnight, and there's a lot of engineering and thought processes that have to go into this. This is atom interferometry timeline, lab studies to commercial applications. This one took from, believe it or not, 1991 all the way up to 2020. That's how long this took to mature. Here's another example. They've got a thing called magnetoencephalography, and it shows over here in the right-hand picture, this guy's got these sensors up to this kind of skull cap thing on his head. This is the only humor slide I put in here, but because of global geopolitics, I thought, well, maybe it'd be fun to add some levity to the presentation, but you get the idea. This is a famous U.S. president and a famous Russian president. There is a technique, and I'm sure people on the conference, like Dr. Taha and Dr. Alain Chancé, know about this. It's called nitrogen vacancy center magnetometry, and this is another advanced form of quantum sensors here, and the narrative explains it right there. And then there's also something called quantum optical effects, and this principle is used in something called LIGO, which is laser interferometer, gravitational wave observatory. And again, this gives a timeline here so that you can see how these techniques evolved. Okay, so here's some more stuff, and this was actually provided to me by Dr. Alain and Dr. Taha. This is more quantum sensor stuff. This is from their presentation that they gave back in November of 2024. And Dr. Alain got to see an advanced copy of my presentation. So, well, I think you would do well to add some of the stuff about AI-driven quantum molecular sensing for cybersecurity. So the premise here was that because the world is connected by fiber, undersea fiber cables, how can you tell if that cable has been tampered with? And so they came up with some ideas with controls, and then how can we measure this to determine if the cable has been tampered with? So they came up with an idea to use carbon monoxide as a quantum chemical sensor, and basically just did the formulas and then proved it out in a lab and used AI to simulate it with physics-informed AI packages. So it's quite a this is what Dr. Alain and Dr. Taha with MolKet are world-class specialists in, and they come up with methods that basically it's like laboratory and theoretical, and then they go prove it in a lab for their stakeholders. So this is fantastic. This is the best application of math and physics and quantum sensor science that I've seen, and so this is fantastic stuff. Thank you, Dr. Alain and Dr. Taha, for permit me to use this. So this is another very valuable part of the presentation. How do you establish and operate a quantum foundry? Well, you build a strong quantum focus team, and I'm going to get into that in the next slide. Come up with great ideas that people will pay money for. Appoint strong results-focused leaders with leadership skills, quantum skills, and people skills who can build strong learning teams. And learning is a very important thing here. A learning team is different than a regular team, and you'll see that in a second. A solid project plan, and I'm going to give you an example of that. Sponsors and funding, kick off the project and execute your team's shared. So there's a guy, when you just get this and go back over it, please go back and research this guy named Peter Singay, who came up with this idea of if you have a learning team, the team continually evolves and matures and pulls together because they like to work with each other, and this is a very good leadership style. If somebody asks you, what is your leadership style, hit them with Peter Singay's learning team disciplines. That is systems thinking, mental modeling, shared vision, personal mastery, and team learning. And if you build a strong team, you won't have the turnover problems that lesser teams have, and you will save money and continually get better. So this is a very valuable slide. So these are the project phases that if you're going to put together a quantum foundry, you've got initiation, planning, R&D, infrastructure setup, core development, and these are the key deliverables over on the right-hand side. Verification and testing, implementation and deployment, and also auditing and final review. And I've put all this together. So this is what it looks like on a Gantt chart. And it's approximate periods all this would take to get done. So we chose the idea of a quantum sensor foundry, which is what's in our DARPA proposal. And then I've got an example. There is a quantum sensor foundry in Switzerland called QNAMI. And this is actually documentation from their website. They specialize in 5 areas: sensors, that nitrogen vacancy diamond thing, implementation mask, lithography, and reactive ion etching. And I'm almost finished here. I didn't think this presentation would be complete without giving you guys some idea of what the quantum sensor market looks like. This is right out of the State of the Quantum Industry market report that just was done in early 2025. So it's about a $375 million market, and it shows you the growth with all the data that they had going up to the end of 2024. These are some quantum computing use cases to kind of tickle people's brains about areas where they might be able to use some of these and quantum sensor design and manufacturing. This is the composition of the industry as of January 1st, 2025, and it's about a $1.4 billion market, and it's getting ready to go exponential like a hockey stick. The workforce is approximately 14,500 pure play quantum workers and 7,400 that are doing quantum related positions. Here's another workforce slide that tells you which countries or which geographic areas have the most quantum workers. And the workforce by role, and this is a nice donut chart here. It's got all these different roles that are currently in use in the industry for people that are looking at this. This is a very important slide, and this can save you a lot of money if you do this right. This picture with the guy with his hands open here and the glasses, he actually looks a little bit like a mentor that I had between 1985 and 2018. But this guy's name is Ted Hoff. He invented the 4004 4-bit microprocessor that had actually 2,700 transistors on it. And this is his quote: "You can be smart and talented and invent and produce great things, but if you can't demonstrate the business value and market it and monetize it, you're doomed to fail." And when I watched this, it's about a 48 minute presentation. That statement just hit me right between the eyes, because we, all of us who like to play with technical things, not many of us have an MBA. I do have an MBA, but not many people do. And so the idea that, hey, you've got to invent something and make a profit from it, that doesn't occur to a lot of people. So I encourage you guys to go look at this video and hear him say this. And this is one of the most important guys in 20th century technology, because if we didn't have a 4004 CPU, we wouldn't have the i7 and i5s and all these other processors that came along afterwards. So these are the conclusions. Rapid advances in quantum physics and quantum science have led to the creation of quantum computers and quantum sensors. Using tools like quantum computers and quantum sensors, we're now able to compute things and measure phenomena in ways that are helping us discover more science and in shorter periods of time than we ever imagined. One essential component of this is to build quantum foundries, and the more organizations discover efficiencies and successes that result from quantum foundries, the more it's going to become the preferred method of manufacturing. And I've got a little quote here that I love from William Gibson. This guy's a famous cyberpunk author, and he actually coined the term cyberspace in the book Neuromancer. And it says the future is already here, it's just not evenly distributed. And I firmly believe that. So I'd like to open it up for questions. Have people got any questions or anything they'd like to discuss about this?
So thank you very much, William, for this nice informative talk. I know that the time was short, so you couldn't explain all of it, but that's a very wonderful indeed resource for Quantum Foundry and how to establish Quantum Foundry for quantum technologies and quantum computing. So we have time for, I think, one question or and a half. So yeah, hopefully, okay, please go ahead, Agent Tariq.
Hey, thank you for this valuable presentation. I would like to ask about quantum sensors used in quantum healing and detection of the body status. Actually, I'm an ex-employee of PerkinElmer International. I spent many years working with spectrometers, atomic absorptions, and so on. Then I moved forward to IBM and then back to scanning electron microscopes and so on to catch the nanoscience and nanotechnology. Now I'm working in quantum healing. And I wonder if there is some advancement to detect some crucial parts in the body, like the mitochondria, for example, the electron transport chain, and how the energy flows inside the body. Actually, in a diabetes case, many people don't know that there is a sensor in the pancreas called the insulin sensor. This can block the feedback of the pancreas, and then the problem of diabetes arise. So if you can elaborate, I would be so grateful in this.
Well, I've always been a science geek, and I encourage everybody here, if you like biology and science and human physiology, to go watch this movie that came out in 1966. It was a dramatization of Isaac Asimov's book, Fantastic Voyage, and the premise was that they took a small submarine and they shrunk it down. That this is nanotechnology before anybody realized they could do that, but they shrunk it down and then they injected it into this guy's bloodstream to go take a blood clot out of his brain. So it's a fantastic movie and idea. I firmly believe that the science that is getting explored, because we have these new technologies with quantum sensors, that exactly what you said about we're going to identify problems in biology and human physiology, and then we're going to design methods to custom tailor solutions to heal people. And as fast as technology is advancing, I'd like to think that what I just said will actually be a real solution within the next 5 years. I don't think this is 50 years away. I think it's 5 to 10 years away. I really do.
Okay, so thank you very much, William, for the nice talk, and thanks everyone for the attendance today. I would like also to thank Engineer Youssef Eldakar for the participation. I don't know if you have any concluding remarks about the event. So I would like to thank everyone, and also special thanks for Alexandria Library for the organization, and that, yeah, Engineer Youssef is with us. Yeah. You are mute. Yeah.
Yes. Yeah. Thank you, Dr. Taha, and thank you to all the speakers. I think today was really excellent time and very dense and rich. And we look forward to continuing our journey and to be hackathon toward the end of the summer. All the best, everyone. Thank you.
Guys, real quick, write this URL down, because after June 2nd or June 3rd, you'll be able to have a copy of the presentation.
So please feel free, everyone, to note down the link. Yeah, hopefully everyone had made a screenshot of it. So yeah, thank you, and thanks everyone, and we're looking forward to see you again in the upcoming series next month, and also thanks also for Youssef Eldakar for the organization, and also in the organization of the hackathon that's gonna be established in September. So please feel free to subscribe, and also, as he told, there will be another beautiful program that will be a summer training for 2 or 3 months in Egypt, led by Dr. Ahmed Yunus. So also, if you are an undergrad, please feel free to ask him about how to subscribe, and that is going to be a very useful program, because you will be immersed for a few months in quantum and the quantum technologies. So you are going to learn a lot about quantum algorithms and computing in general. Okay, so thanks everyone, and wish you a really great weekend.
Thank you very much.
See you on the next edition, and hopefully eventually see some of you in Alexandria at the Library of Alexandria in September.
Fantastic. Thank you, guys.
Yeah, thank you.
Bye.
Bye-bye.
Bye-bye.